I think we are at time, if I'm correct. Welcome to this tutorial, the Planetary Causal Inference workshop. My name is Adel Daoud. I'm a senior associate professor here at IS, Institute for Analytical Sociology, also affiliated with Chalmers University and Data Science and AI division there, where Marcus is at. If you want to say a couple words about you, Marcus, as well.
PhD student with Chalmers, working more on the computer vision side of the projects. Adel was my supervisor. Yeah.
And now it's a reverse situation where the supervisor presents. And we have also Connor Jerzak with us online. Connor, if you want to introduce yourself.
Yes, thank you, Adel. Great seeing everyone there. I'm Connor, and I've been working with Adel on some of this work on planetary causal inference. So we aim to bring planetary scale analysis together with RCTs and observational studies to squeeze more juice out of existing causal inference pipelines in that way. So looking forward to discussing with you, sharing some code, sharing some ideas, and so forth. So I'll throw the ball back to you, Adel.
Thank you, Connor. So with that, I would like to just sort of get to know you a little bit better. So by show of hands, how many have a background in computer science? A couple. Data science, roughly like overlapping. Yeah, cool. Social science. Yeah, so what would be like econ, political science, what discipline? Just shout it out. Sociology. Okay, cool. Social science. Yeah, cool. Yeah, great. Someone else, social science? International relations. Cool. Very nice. Yeah, so great skill set and great background. Really, the planetary causal inference idea is sort of born out of the research environment at AI and Global Development Lab that is a research, as I said, a research environment between the collaboration of here at Linköping University, the Institute for Analytical Sociology, Chalmers University, where the computer scientists mainly sit. We have Connor at Texas, with some hip students. We have also people at Harvard Statistics with Professor Zhaoli Meng there. And really sort of how this group came about was during my time at Harvard, where I was a postdoc, was basically to think about, it was a lot of research going on, obviously in NLP at that time, with some causal inference. And the questions I was sort of asking myself, my background is in social science, specifically, global development, political economy, is how do we, bring what's sort of happening in computer science and data science in general to the social sciences, right? Specifically my domain, but maybe also sort of broaden it. And so I was writing this grant for the Swedish Research Council. Actually, it was for the European Research Council first, the ERC, that unfortunately I didn't get, but I landed instead at two major Swedish Research Council grants that sort of helped found the group, where we, today basically sort of a consortium of collaborators with multiple grants, where we sort of join together under this sort of umbrella of thinking together from like, how do we translate computer science insights, statistics with sort of the domain focus on global development, broadly speaking. Now, as you will see in this workshop, much of what we are going to talk about is, branded around remote sensing and Earth observation data. But as you'll sort of realize very quickly, this could have been robotics, medicine, could have been basically, any type of domain where image data is prevalent. So again, just by a show of hands, how many have a background in remote sensing? We have one. Okay, cool. Image data? A little bit. Okay, so good. So some of this stuff, like, I've basically set the baseline for some of the insights of this workshop is for social scientists who have basically never touched an image object, right? So it's basically at that level. And then I'm gonna quickly sort of run into the domain of causal inference. And really what I want to sort of take away from this for you is basically to see how would you sort of very quickly, rapidly come up with a pipeline to answer certain questions that you're interested in. Now, before I go on, if you want to sort of direct your phone and with the camera, this will take you to the Substack email address. You can just sign up if you're interested in keeping in touch. Some of the workshop material, I mean, all of it will be posted there. It's also on the lab website. I'll show you in a minute. But it will just basically be in a constant way of keeping up to date with stuff that we're doing, but also a way for you to reach out and track our work. Great. So as I said, all the material is under sort of the development, AI Global Development Lab repo. We have the Substack. I'm gonna, after this workshop, write a little article there, upload all the material that I have in terms of code and slides. It's also gonna be available at the book website, the Planetary Causal Inference. Also want to do a quick shout out for the causal images package that I'll be talking a lot about towards the second half of this talk. But basically, you'll find the public repo under this link, and the development repo under Connor's personal development GitHub accounts, organizational accounts. Good. So 2 parts. Basically, the first part is going to focus a bit more about sort of intro to image data. How do we think about images? And I believe a lot of us have a background in NLP and text analysis. And I would say, like, 10 years ago, NLP was, at least in social sciences, sort of like really starting to take up, and it was sort of the new thing. Now it has come to a stage where it's everywhere. Like, the LLM workshops, everyone is using it, and it's at some stage it's going to be standard, if you like. Well, our hypothesis with this workshop is that images will have the same sort of peak, but right now it's sort of a little bit, NLP is ahead, and then it will be image, and then it will be multimodality. Essentially, in the end, it's not going to be a matter of whether you do text or images or audio or whatever. It's really sort of thinking about multiple sensors jointly. So I'm going to talk a little bit about image data in the first part of this. And roughly speaking, I'm going to spend 60 minutes and give and take 5 to 10, 15 minutes maybe on the just importing basic image objects into R. And I should say also, why are we using R? Everyone is using Python more or less, right? And in this domain. I mean, this is another hypothesis of ours, is that because we are targeting much of these ideas, this framework for applied social science, is that most of those people will be more familiar with R. They have, a lot of pipelines up and running already. They know how to handle these objects. Python is becoming more of a standard as well in social science, but it wasn't like, 3-4 years ago, I would say. So much of the work that we're doing is going to be a bit overlapped with what you see in Python, but it's also, for sort of a way of creating these infrastructures in multiple languages. That's sort of part of the implicit goal. And that's what causal images is trying to achieve here, is sort of translating some of these functionalities into R. Now, as you would know, you'll still have to rely on Python because R doesn't natively run these big models, so you need to basically call Python through R. So you can't really do away with it. But until sort of Python becomes the standard, I believe there's the big chunk of a need for having something like causal images up and running here for this domain. So second part is going to focus heads-on on causal inference. Think about causality through the lens of images. I'm going to do some parallels to text data. But essentially, if actually, just by show of hands, causal inference, how many have background in causal inference? Okay, some people. All right, good. And so if you're in causal inference and in machine learning, you know that high-dimensional data you can handle in a variety of different ways. And in the end, it doesn't really matter if it's text or image or audio. You can sort of do causal inference with whatever, okay? But the particular sort of data type will still condition you to think about computer vision in a particular way, because image data still have its own sort of interesting sort of modality to think about, okay? So that's the setup. And also, at any time throughout the workshop, just stop me. Don't wait until the end if you have questions. This is meant to be an interactive workshop. If there's anything you are wondering about, just ask. I should say we're recording this, and I'm on a microphone. Your voice won't be heard. I will repeat your question, so you'll be sort of anonymized through me if you're worried about that. But if you nonetheless don't want that, to be recorded, there's no video here, so you won't be seen. Just let me know, and we'll figure out a way of taking you out of the picture. Okay, does that sound good? Fantastic. Great. Let's get started. So talking a little bit about the conditions. So like, where do you stand in terms of like coming to this? What kind of skill sets would you need to understand and follow the workshop that we're gonna go through today? Well, I'm gonna focus a lot about, as I said, handling image data and using sort of thinking more conceptually about the pipeline of doing causal inference with images, specifically satellite images. And for that, you'll have, some R background basics would be good. Basically, causal inference basics would be great. But if you don't understand anything, do stop me, and I'm happy to define whatever concept that you are wondering about. Some geospatial analysis would be sort of advantageous to be able to work with sort of GPS data. But actually, much of the code that we'll be sharing with you, some of it is simulated, so it'll be quite easy to follow. And other of it is sort of following a particular 2 papers that we have written. Both of them are under review. So some of the data we'll be able to share with you, but not the full data set until the paper are fully published. But those are actual experiments focusing particularly on aid development programs in Africa and their effect on poverty and inequality. So what will we not cover? I mean, there's just a lot in this domain, right? So we won't be walking through like how do you fetch images from, say, Google Earth Engine. And there's a lot of really great tutorials on that on Google Earth Engine itself. And also the European Space Agency have a similar one. So there's just a lot of tutorials out there about how to fetch images. We really want to focus on the intuition rather, like how do you, given that you have an image, how do you actually think about causality here? And what general sort of challenges would you face with it? And it's important to sort of take a step back as well and think about what we're doing with high dimensional data from a perspective of low dimensional data. Sort of think about it from the basics. You have random variables, there are relationships between them, and you're interested in certain sort of causal effects. But how does this high dimensional data actually rise in the first place, right? Why does it even exist? What's the relationship to the rest of this sort of big joint distribution of a causal system that you're interested in? And once you have that intuition in place, I believe it's much easier to sort of play around and understand like where these high dimensional data fit actually in your pipeline. Great. So what is planetary causal inference actually here? So let me just put this like this. So really, planetary causal inference is more of a methodological framework to leverage satellite images, Earth observation in general. And here, together potentially with other modalities, particularly tabular data and text data, you think about how to analyze certain sort of processes on the surface of the Earth, right? In a way, they have to sort of play out on the surface of the Earth, and that playing out, that interaction has certain effects that happen and then sort of imprint itself on images. And the idea is then, how do you, through the lens of these satellite images, actually discern cause and effect? So in a way, it's sort of a subset of a general research agenda that is unfolding in machine learning in general and computer science, which is sort of called causal representational learning, if you like. I mean, causal representational learning, to some extent, if you haven't heard that term, it's about sort of finding those low-dimensional features from that high-dimensional processes to discern cause and effect. Here, we sort of not focusing on that causal discovery part. We sort of, as you will see, assume a lot of structure on the causal process that is sort of important from a social theory perspective. Sort of as a social scientist, we care about social theory, how X and Y are connected through which mechanisms, and so therefore structure is very important. So you might say like, okay, cool, that's interesting. So who is in this space? Well, if it turns out that if you do a search, sort of a literature review looking at Earth observation, sort of remote sensing, causal inference, and development, you do find a subset of papers here that is sort of emerging. I would say it's like an emerging literature. It's still not taken off in a big way, but it's also an exciting way. It's like if you think about being a researcher, it's like being an entrepreneur in a way. You want to sort of not do what everyone is doing now. You want to sort of look up a little bit and figure out where's the field moving, so that you can sort of tap into that and make an effect in terms of innovating the intellectual space. So you might say, but it could also be like a risk, obviously, from an entrepreneurial perspective, is that maybe it's not taken off because, you know, there's a reason, like, you know, maybe it's not interesting enough, right? But as you'll see, and hopefully I've already enticed you, that there is a lot of potential. I mean, if you think about satellite image data, how many, you know, petabytes of data that is sort of sitting there waiting to be analyzed beyond agriculture and environmental studies, you soon realize how much value these things will bring. Right. So in our lab, we have been, you know, particularly leading basically two arms, more or less three arms, if you like, the applied side that brings all the insights from the methods development. We have the measurement side that thinks about how do we actually measure processes in images, not necessarily doing causality, but doing forecasting and measurements of, say, poverty trends. And then the other arm, which is thinking a lot about causal inference. And so in this space, we have these particular articles that we'd like to highlight. Please.
Are the main reason that the field is potentially taking off now?
Yes. So the question is basically, what is the reason that we believe that the field will likely take off? So I would say there are a couple of things that will play on. One is obviously the availability, the public availability of satellite images and high resolution imagery that is, you know, even through Planet Labs and Maxar that have sub-meter resolution pixels. We basically can see what kind of car is standing parked outside of a building. Is becoming more and more freely available, at least for educational purposes. Will just, you know, yield a lot of information that you could actually leverage to study inequality, say. I say compute is another. You know, we have, you know, basically at Sweden at least, we have this free public resource for universities that you could run these big models with expensive GPUs, essentially freely with some restrictions. That's number two. And I say number three is also the integration of social sciences with data science in general, that you see a lot of there's a willingness to take a leap to try new methods from sort of traditional social science. And so that will enable us to sort of start using these things at scale. The massive amounts of foundational models that are actually trained on Earth observation data is another sort of facilitator, so that you don't necessarily need to run big models yourself, I would say. So several things that are converging here to a nice eclipse of potentials. So yeah, it's a hypothesis, right? And it's a matter of time. Please.
Because actually me and my colleagues are also like doing the opposite direction.
Yeah, okay.
Because we are there in our field called sequence analysis, which is a life course studies method, and then it's more like existing methods are all based in R.
Yeah.
But it really has constrained a lot if we are going to use like a large data sets. For example, the R program just crashed. So that's the reason why we're doing our Python version.
Yeah.
So
Great. Yeah.
about the data.
Yeah, I mean, there's definitely trade-offs here, right? I mean, one way is I'll show you in the code, for example, is that you won't be able to load all the images into our memory because it handles it in memory. So instead is that you'll create a sort of a memory mapping that Marcus can tell you all about. Like basically you map as if it was in RAM, you know, but you have it on hard drive and it loads in sequentially, like when the data is needed. So that ways of handling large data in R that makes things easier for you. So it's, I'm going to show you some, you know, it's a bottleneck that R needs to rely on Python. That's definitely a bottleneck because you still sort of need to know some Python to be able to use this. So you might say, hey, but isn't it better for me to just do Python? Well, I would say if you are, you know, knowledgeable in Python, you want to do it, go for it. It's great. I mean, it's just a fantastic language. It's more of from a serving perspective, we're thinking about it like, yeah, we could definitely use Python ourselves and we use Python all the time. But it's how do we serve a community of potential users that aren't maybe willing to make that leap as of yet. So it's more of that from that perspective. So if you as an individual researcher think, hey, I can run with this and I can do my own thing in Python, great, just do that. So does that make sense? Yeah, yeah, yeah. It's maybe like a serving intention rather than like a me as a user intention. Yeah. Great. Connor, do you want to add anything to what I said?
No, I think that makes sense. I think, this is work in progress. I think the long-term vision is to have interoperability, since there are a ton of great packages that have an R version and a Python version. And ultimately you can run R in Python and Python in R, but it's probably better just to have a native version of each. Although the R version will depend on some of the computational tools that were originally built for Python. So for example, causal images relies on something called JAX, which relies on some sophisticated optimizations and compilation strategies that R currently doesn't have access to. So big picture, we are looking to add support for both. Right now, it's an R interface with a Python backend using JAX. But ultimately, supporting both makes sense, since there's a big community in each, and I think the two communities are a bit different.
Yeah, definitely. It's two different communities with different sort of skill sets and different willingness to invest in the actual tools. They're more interested in domain usually, right? So like if I'm a development economist, like I might, I mean, very good at Python, but I might not. Like I use my Stata because all the code is like in Stata and I replicate it. So I'm used to that. So from that perspective, like we can make it easier for them. It will be a way of extending this research area to them. Cool. So Planetary Causal Inference, the book. So essentially, much of this research if you think about taking a step back, like all this research is happening around us. We're doing our research and we're sort of creating a lot of really interesting products. How do you consolidate that idea? And how do you, take what has been learned in terms of those insights in the research lab particularly, and create something of a usable sort of, basically encapsulating that wisdom in some kind of book. So the Planetary Causal Inference book is trying to achieve that. So what we are doing in this setup here is that to say, right, so we have potentially many different aspects of Planetary Causal Inference. We have the confounding that is this workshop about. We have the measuring the outcomes that I sort of mentioned just recently. There are many different aspects in terms of how to handle data. I think about the modeling. And so what this book is trying to do is sort of handling that complexity of different topics is to basically boil it down to recipes or ingredients and recipes. So we have a cookbook of planetary causal inference. So here, then what we have done is basically taken our sort of different articles that we've written and then break it down into different chapters. So the first the first part is encapsulating the ingredients. And essentially what we're saying, there are always 4 or 5 different ingredients that you need to think in terms of causal inference with image data and other modalities. You need, you need to think in terms of the research question, obviously. And that's a sort of the key thing from a social science perspective. What is the system that I'm studying, essentially? How do I sort of draw it out? That's what chapter 1 is sort of setting the question, and then therefore also the estimate. It's so easy to get bogged down in all the modeling and all the processes if you don't know exactly what quantity of interest I'm interested in. I'm going to show you exactly what I mean by that in the coming slides. And then after that, basically the setup here is to talk about image data and Earth observation data in particular. That's sort of the second ingredients. And here, as I sort of alluded to earlier, this could have been basically any type of image data, in fact. It could be medical image data, it could be robotics, it could be fashion, it could be many different types of domains. But also critically, what we think about from a causal inference perspective is that we really care about how the variables are measured, the sampling, and the uncertainty they yield. So this sort of brings back some of the core intuition for statistics, is that how do we think about those uncertainties playing out in this process? And then obviously causal inference is a key component here. 5th is machine learning in general and computer vision specifically. And what we're going to do here, and again, this is the audience is really thinking from a social science perspective, sort of applied quantitative social scientists would be the key audience here that we are targeting this to. And lastly, and this is actually, as you would know, quite important in terms of compute. Now, how do you write a chapter about hardware? It's not going to be easy, but it turns out that there's actually a lot of sort of rule of thumbs to think about in terms of, I mean, you asked the question about like hardware, you know, in terms of sort of loading into memory versus having it on hard drive, thinking about like the GPUs, how does this actually, you know, how do they actually do matrix multiplication in GPUs? Why is GPUs better and worse? It turns out that there are some kind of intuition that you can distill down. And this is sort of what chapter 6 is going to focus on. And then what we're going to say is that, you know, depending on the ingredients sort of that you bring, you can start sort of targeting different types of or if you like, recombine different elements to create this sort of recipes of cookbooks, where the first one is going to focus on what we call remote surveying. In a way, it's measurement, but it's remote because it's done from a satellite image. And we're going to observe the planets, and we're going to ask, you know, what happens there, and what can we measure, and what can we not measure. So much of this work on chapter 8 has been led by Marcus, is to think about, you know, poverty prediction in particular. So in Africa, we have lack of survey data, and particularly now with the dismantling of US aid that has been financing a lot of the measurements and high quality measurements in Africa and around the world, is that there will be a lot of sort of demand for more data. Even when the DHS was around, there was a demand for these data. The question is that how do you create machine learning derived products and make them usable downstream? And that's sort of what chapter 8 is going to be about. Chapter 9 is to think about exposures. So I'm thinking about, like, you know, not only can we measure the outcome, we can also measure different nodes in this process. So for example, if you think about the building of roads being important, and you don't have a road data set, and actually that is there's a lack of a temporal road data set and globally, then you could think about, can I train a model in a particular way that helps me measure this connectivity of infrastructure at the planetary scale, and then use that as my treatment in a downstream analysis. Then comes part 3, where we think about observational studies, sort of how do we recombine what we've learned from the previous parts and also the ingredients, such that we can now use the outcome in a downstream analysis. And some of the results that I'll show you later on in the workshop is actually derived from these machine predicted poverty outcomes in Africa, and then we're going to use them downstream. Now, some of the problem here is that you have potentially bias downstream. So how do you upstream, sorry, in the creation of the model? How do you debias that, and how do you quantify uncertainty in this pipeline? So there are potentially many other different sort of chapters to be written here, but the idea is sort of to recombine and create recipes that are reusable. So we're not fully exhaustive, but we're sort of giving you a roadmap for how to think about planetary causal inference in this setup. Now, the part 4 here, which is actually quite interesting. So much of what everything that we'll be mostly talking about today here is about observational studies, where we use images as a way of proxying these unobserved confounding. But it turns out, and what these, we have basically 4 or 5 different chapters to show you that you can use these images even in randomized controlled trials and field experiments to help you do and conduct better experiments. So one of these that I would like to mention is chapter 16, remote audit here, where we can basically search for potential selection bias that is happening in this process. So how does this happen? The intuition is essentially that images shouldn't matter for the selection of where I, as a, say, experimenter, is putting the next experiment. Imagine a couple of villages, I'm in Africa, and if I randomize correctly, I've randomized away any effect, any background variable that might affect my treatment selection, right? But if I, maybe favor some villages over other, maybe when I'm, as a development economist, went to Nigeria and said, I want to run an experiment here, can I do that? maybe I was influenced by policymakers say, yeah, but maybe if you run a little bit more in this village, in this region, than that region, then you start seeing traces, of potential differences and potentially even in the regional sort of geographical makeup of these units. So what will happen here is that sort of we're searching for a signal where a signal shouldn't exist. So if the randomization worked perfectly, essentially there's no signal. So the feature space of images should be identical for the treatment and control. If there is signal, it means that essentially you'll have a model that is able sort of to discern differences, at least that exist in the image space, right? There might be other ways that this bias manifests that doesn't sort of show in the image. But if it shows, which is quite likely if there is sort of geographical selection, then you can sort of actually sort of say that there's some kind of a threat to the randomization process itself. Transportability analysis, I think, is another really interesting aspect, is that imagine you have an experiment, you have sort of figure out the effect and you're happy about the results, but it was so expensive to run, and so you aren't able to replicate this experiment at scale. Is it a way of using the image space as a way of generalizing? So imagine that, I ran in these villages, this field experiments, and I found this interesting, really important effect of giving, say, medicine to some villagers and not others. And the effect of this medicine was actually really salient. Then you could potentially think about heterogeneity also in this sort of image space of saying, yeah, the reason this sort of effect was playing out in this particular way was partially, correlated with how the geography looks like. Basically looking for heterogeneity effects. So imagine instead of looking at whether gender had an effect, you can look at basically the image feature space having a way of an effect of moderating this causal effect. So essentially what we're saying, you have a pipeline of planetary causal inference toolboxes that you can apply to measurements, to observational studies, to field experiments. And what this book is going to do is essentially encapsulate this knowledge in this way that we set it up. So this is basically just an overview of what this book is about. And I'm just very curious to hear, is there something that you think was left out that you would have loved to see more of or less of? Yeah, just shout out what you think. Please.
I'm not coming from the image space at all, but like, what's the intuition for like, what are the interpretable aspects of images that would be in something like selection bias?
Yeah.
What are you actually trying to pick up?
Yeah. Exactly. So I'll have a couple of slides on that question particularly. So, but I'm going to give you an intuition. Essentially, the idea here is that you can think about there being both observed and potentially latent information in the image. Observed would be clearly, say I can see mines from images, which you can actually see open sort of air mines. And then you see that it's an observational studies, and you sort of figure out why are Chinese development projects or World Bank development projects being located closer to mines? I mean, or is it maybe potentially so that they are? And if I don't have mine data, then I can use the images more directly as a way of sort of proxying location of mines. And so that would be an intuition, right? It's sort of an observed feature. I can see it. There's a resource, and I'm basically adjusting for that resource without actually having a label for it. So that's one intuition. The second is that even if you don't see that feature, the mine in the image, images can carry latent information that is actually important for the adjustment itself. So take the mine example again. So say that I can't actually see the mine, but I can see that the patterns around the mine, they look like something is happening. Like there might be some signal of what the mine leaves in the image that is not for the human eye sort of directly revealing that that's a mine. But that systematic signal, the algorithm will be able to detect.
Air? Or like what?
Magic. No, but essentially, so I'll take the poverty example. So what we're doing with leading with Marcus and some other lab members is that we measure poverty, right? So we have outcomes of the number of television that is in the household. We know the number of bicycles that they have from survey data. Okay, so none of these we can see, right? We can't see bicycles from an image from a 30-meter square resolution image. Neither can we see the cars. We can't see what's in it, even with a high resolution imagery, you can't see the number of televisions. But what it turns out that the way, the number of televisions, the bicycles, the type of flooring and so on correlates with how the neighborhood looks like, tend to reveal the poverty sort of level, or maybe I would say the wealth level, the health and living conditions level of that neighborhood. And that, it turns out that the algorithm is able to detect. And so it's actually really good in detecting these health and living condition outcomes of an R square of 0.75 approximately in held out data. Yeah. Yeah. So it's really high prediction rates, which then says that there's a latent sort of space where these features are correlated, such that they're actually yielding important information towards, picking up on this outcome at least. But that's actually the key intuition that you were asking, like, what am I actually looking for? What's going on? And so maybe what I'll do is that I'll speed up a little bit, because there's also an intuition about maps that I want to come to. But before I do that, actually, there was one question about confounding. Is there anything else about like the idea of the book? Because the book is sort of in the making. We're writing this. I mean, this workshop is part of trying out the material, and it will be for us a better way of sort of writing up the key chapters. Anything that you would like, or?
But from the statistical standpoint, I would be very interested in understanding more about the uncertainty.
Yeah.
Even though the accuracy rate, as you said, is already quite high, but
Yeah.
I kind of feel that it's still maybe it's just still hard to avoid something. There's some
Yeah.
interested in knowing more about how you can measure.
Yeah. Okay, I'll write it down. So uncertainty, I won't give it to you now. There's a lot to say about uncertainty, but let's come back to that. So I'll write it down. Like, you want to know more, like you would like to see more about uncertainty in the book. Yeah. Okay. Good. Yeah.
For the machine learning, they mainly talk about like accuracy and benchmarking and
Sure.
things, but I can feel that the traditional statistical standpoint is still
Yeah. Absolutely, yes. And in fact, statistical, like any inference, is about like bounds, like knowing am I within or without with the sort of the bounds that my estimate is within. It's a great point. Anything else that would you like, please?
Just regarding the unit of analysis, or maybe how do you choose the boundaries of the units that you're analyzing later when you feed it into the causal inference pipeline? Like, which regional scale do you use, for example? I think that's kind of often a key question of this. When it comes to using this data, can I aggregate them into like neighborhoods or regions or cities or metropolitan areas? And how to do that in a way that you don't bias your results, because the way you choose the regions also has a big impact, I guess, on your later analysis. Depending on how you draw the boundaries of the geographical units, this also matters, I think.
Yeah, it's a good point. Basically, selecting the right resolution for the analysis, so we can basically create these ecological fallacies if you don't. Yeah, great point. Okay, good. I mean, if you have any other thoughts, we're always happy to hear them, and do reach out if there's anything else that sort of pops to your mind. I should just make another advertisement for another book that we're writing, which is The Trinity of Statistical Learning. Here, the idea is really about data science and the sort of age of multimodality. So here we think about multi-source. It's not only images, it's also text, it's also tabular data. It's talking about what you mentioned of different resolutions. So you have units from households to clustered in admin regions and higher political regions and countries and so on. And also there's a temporal dependence. How do you think about that jointly? And so we have this course called Stat 288 that concluded for the fourth time now at Harvard Statistics and Chalmers where we sort of have that as a sort of a base material for that writing of the book. Good. So back to the question of what do images give, and what's the intuition of using images as confounding here. And I say that this policy brief written by the World Bank, it's basically titled "More Than a Pretty Picture," and here the subtitle is basically using poverty maps to design better policies and interventions. It sort of almost says it all. Essentially, geography and time is everywhere. So when you think about development officials, allocating different projects, where to build the next road, where to build the next, urban project, how to think about urban development, sustainability, you think about maps, right? You look at maps. Maps are involved somewhere in the process, right? I bet you everyone here used the map when they were trying to find this location, for example, if you've never been to Norrköping. My job is here. I will still look on maps when I'm in Norrköping to find restaurants and other places. So basically, maps, play an intricate role into human behavior and human sort of interaction. And so then, if that's the case, well, it's likely that satellite images carry a lot of information about how humans interact. So that is sort of the overarching intuition of why images, likely are important. And I should say, we don't have access to those maps always. Like sometimes we do, but images sort of play the role of a substitute. Like we might actually want to have those maps to see exactly what the human decision maker looked at when they decided to build a road here or there. But image data, as it turns out, becomes a really sort of close proxy in many ways, and also a higher dimensional proxy that allows you to more than just searching for this sort of map intuition. But the map intuition is important, but it sort of is not exhaustive. So even, if you think about segregation, inequality research, like tabular data, as in Sweden, for example, we have the Swedish registry data it's an amazing data source. It exists, openly for research, and since the 90s, essentially. But if you think about what happens within a year, potentially seasonal effects or even historical effects, actually, you don't have that information encoded in registry data. So even there, satellite images sort of can proxy that role of seeing basically, growth of urbanity and also like urban cities connecting to each other and over time in space. So the way that we sort of started to work in this field is definitely thinking about data scarce areas. I mean, that's the easiest to motivate why you would need to sort of run with the hassles of satellite images. But it turns out that, even in data rich areas, it sort of is a great proxy. And okay, so let's talk about like what is a satellite image really here. So if we go a little more hands-on, and the best way is really sort of to look at what satellite images capture. So this is a sequence, basically a video from 1984. You see at the bottom, it's basically deforestation in the Amazons in Brazil. And this is basically, you don't see humans, you see the effects of that process, right? And it's a powerful sort of image showing, what effect these, and it's almost like ants having this sort of effect on the planet of sort of depleting resources in terms of these forests. You can think about coastal expansion. I mean, I love this image for the reason of it being so artificial. Like this is the coastal expansion, and then you basically see something very artificial popping up. And this is just purely from the image space, right? And thinking about urban growth, Las Vegas in 1984. I mean, it was a very small town, right? But then you look at it and it sort of grows. And you see these processes. And immediately for the human eye, this sort of makes sense, right? We understand it. There are no labels there. And I talk about that, and you look at it and we understand what's going on. So the question is, if we understand what's going on, to what extent can we train computer vision models to sort of encode that information that is important for the social process? So, and you might then ask, okay, great, but so how can I, not do this with regular tabular data? And, how does it compare with other modalities? I mean, in fact, you could have sit down with research assistants and code it up like, where exactly deforestation is happening manually. You could have done that. It's like as we did in text, but now, we have these big models that are able to help us with that at scale. So these processes are happening at scale. It's very expensive to code up all the data here. So you definitely need some kind of an interaction, very similar to what has happened in text data, but now in image data, so that we can sort of label up, segment images, and make them segments sort of semantically comparable. Now, let's see, is this in the way? So yeah, basically what you see in the top. How do I click this away? Right. More. And then hide, control. There. Video panel. Floating. No. Oh, that was Connor. That was the wrong one. Show video panel. This one? Yeah, there we go. Okay, good. Thank you. So that I don't disturb you too much. All right. So just looking at roughly speaking the sort of the differences of tabular and text and networks and Earth observation. I should say none of these are sort of competing. They're all sort of trying to target different things in a complementary way. But it's just good to know what kind of things they tend to be good at. Okay, so if you think about basically the columns here, I mean the key thing of sort of Earth observation data that for me is sort of is really critical is really sort of almost at the end, is that it's almost never missing except for clouds. The clouds are our biggest enemy. So if you go out and you're sad about it raining, you should be sad for two reasons. It's raining and data is not being collected. Okay, those are the two reasons. Satellites can't see through clouds except for special types of satellites that have radar on it. They can actually penetrate clouds. Okay, and also the number of sort of measurements. So the typical temporal resolution for something like Landsat is about 16 days. It depends on where on the planet you are, but you just have a lot of recordings. So this little spot here, this place has been recorded, basically every 2 weeks within a year. So approximately 24 times there's an image for it. Your house has 24 captures approximately every year. There's a lot of data. So there's a lot of information going on, and it's publicly available. And so for me, is really sort of the key thing is to think about how these things intermingle with the rest. And tabular data tends to be the most expensive to create, right? That creates sort of requires annotation, requires systems. Earth observation data, you might say, hey, it's free. It sounds like too big a true. Yes, obviously someone is paying. The governments are paying. They're collecting the data. So if you have policies that are similar to what's going on in the White House right now, you might not have satellites. Obviously, we haven't always had satellites. It requires it's a public code that requires resources in its own right. So I think it's sort of an interesting contrast that gives you a sense for sort of the richness of the availability of data. Satellite data as such. Now, I realize that I'm going a little bit more deeper than I thought into certain things. I'm a little bit behind on time, and I want us to take a break soon. Do we know when coffee's served? Yeah. I see. Okay, just want to make sure that you don't miss coffee, or if there are cookies. Are there cookies? I don't know. So okay, we can open cookies. So yes. Okay. So what do we say? Shall we go for another 10-15 minutes and then we take a little break? Says 3. Okay. All right. So let's. Well, we might need a little stretcher before that too. All right. We'll figure it out. Okay, so just going back to really basic. So what is an image? How does it work? Well, in a way, if you think about an image, and it's sort of interesting when you sort of get to know what text data is and data representation. Everything ultimately is a matrix, and that's sort of the takeaway of whether it's an image, whether it's an audio file or tabular file. But really, images at least the colored image consists of what we call these bands, right? And these bands basically capture colors. Colors are light. Light is frequencies, okay? And so if you think about like, how do I sort of encode color in visual sort of perception, and then basically subdivide these colors into these sort of base colors, the three colors that are important, the red, the green, and the blue. And that's what we need, three bands. A band is basically a matrix, as you're seeing here up in this visualization. And so essentially you can encode this light information, basically the frequency of light, in a number. And that number you put in a pixel, right? And then those values, depending on how you encode it, regularly they encode it from 0 to 255. But just thinking about it like think about it like 0 to 1, 1 being very high intensity, 0 being the lack of that color, right? And then the way you recombine these colors, you create visuals. And that's sort of how computers are able to see. That's the recombination of it, and that's why you sort of get a color. So if it's a colored map, think about it always having three bands, three matrices of similar size, exactly the same size that you put together that we call an array. Okay? And that's the same thing for what satellite images are. Basically, they take these three matrices. If you want to encapsulate that image of that landscape, you put them together, you get that landscape. And what's important here to remember is that light, light is sort of has a very wide spectrum. So the visual spectrum is very, very tiny. I mean, it's basically living in this tiny space where what the human eye can see. So these satellites, I mean, they capture other bands, other light frequencies that are important for other types of measurement. And so, for example, what you're seeing here is an image taken from work that we did on measuring poverty. Is that we have this is of an area of a neighborhood. So this is the reds, the green, and the blue. You recombine those, you get this RGB band. RGB standing for red, green, blue. Okay. And then you have other types of frequencies that measure what's sort of important for agriculture, usually, or environmental sort of meteorological sort of fields. So the shortwave infrared, for example, as you see it here, printed out, it is really good in capturing moisture on the planets, right? So it is able to sort of see how that light sort of reflects, and it's able to see if it's a very dry or not dry area. And so the thing here to the bottom is night light. So that's what is emitted at night. So of a city, and that's really the cool thing of what satellites are enable you to do, is that you can measure what happens during daylight and what happens during night light. Obviously, night light, you don't get the RGB band, you get luminosity, basically how luminous this area is. And I'm sure that you've heard of these studies, done in remote sensing, where you can see sort of economic development being correlated with the intensity of light. Okay, great. So essentially, you can think about this sort of measurement exercise being an exercise of capturing light, right? And then light doing certain things for you that is important in your process, whether it's environmental, whether it's, just basically seeing what's happening on the planet with a visual eye. Yes, SAR is great. So SAR is I always blank on the acronym, but it's basically this active beaming. SAR stands for basically, it's aperture. Exactly. Yes. So basically, it's an active laser. It's basically active radar. We're not using it ourselves, but it's definitely a potential that could we thought about, but it's sort of. We've been focusing mainly on RGBs, but most of in our models, we're actually including the rest of the bands. Marcus, how many bands are we usually including?
6 or 7.
6 or 7, yeah, in our poverty prediction exercises. Yeah. The thing is with Landsat, and I'll come to this in a minute, is that because it has this wide historical coverage, it starts in the 70s. If you want to build, as we're doing as another data product that we are creating, is that you can see what has happened very far back in time, whereas SAR data has only been around for a couple of years, I believe. So it means that there's some kind of a limits to how far you can take it back. But moving forward, absolutely. Yeah. Only Landsat because of the historical coverage. So Sentinel is also 2014-15. That's sort of when it launched. And so we start our data product in 1990, more exactly. So, and yeah, we're going pure Landsat. And actually, you can do a lot with it for historical analyses. But it's definitely a possibility moving forward if you want to do sort of forecasting exercises. Backcasting exercises, you sort of want to rely on Landsat as much as possible. Right. Okay. So one thing that, at least in the beginning, when I was sort of wrapping my head around this field years ago, was that, you know, okay, so what's the patch size? Like, what's a pixel? What's the resolution here? You know, what does it actually mean? So if you think about what the image is, I mean, if you think about these being trying to capture the same thing, same size it is. This is a spatial resolution of 30 meters, and this is a spatial resolution of 10 meters. So spatial resolution, I mean, a patch is a collection of pixels, and resolution is essentially the size of the pixel, meaning that within that pixel, there is no variation. It's basically whatever it captures, it captures. That's just one encoding of light in that pixel space. It means that, you know, high resolution is obviously, you can capture richer representation of imagery. And this is important because obviously, you know, when it comes to the question of confounding, for example, and measuring other processes, although I made a plea and argument for latent measurement, and it's still there, is that if you do want to capture the number of cars parked outside, I mean, then it's important to have high resolution, obviously. So resolution will be conditioning how well you can do this. Okay. And it's important also to remember that resolution also happens in temporal space. So it's not only spatiality, but also temporality. So I mentioned Landsat, about 24 measurements we have within 1 year. The question is, do you need all of those? Well, it's more data. Wouldn't it be good to use it? Yes, of course it would, but it just then it gives you a sort of a requirement for compute will increase exponentially. Right? So at some stage, you might need to start trading off some of the temporal resolution, some of the geographical resolution. So see these sort of as hyperparameters in your research. But it's important to remember that these are critical aspects that will definitely condition the way that you think about your problem. And also, you know, I mean, if you now put them together, you can think about, like, obviously just as I said, concatenate them, use them all, but also you can think about summarizing them. You know, how do you summarize them in pixel space, each pixel alone? Do you use a filter, try to, you know, basically trying to find something smarter than just taking the mean, right? To respect the geographical, the spatial sort of dependence, both in temporality and geography. And this is sort of, we're now in the domain of computer vision and image processing. How do we represent and condense the information in an image in something that is a low dimensional space that allows us to be a bit more efficient in our pipeline? Okay, so these are just basically the characterization of images, okay? And just to hammer in this idea of resolution, there's this video, you can look at the link later, by this YouTuber that talks about resolution and the human eye that I found really, really intriguing. And how basically, you know, he compares like the brain's way of measurement and how you can estimate what within sort of the human eye in terms of resolution would it correspond to if it was a machine. And they calculated something like 576 megapixels. Whatever that means, it depends on like the angle of how far away you're standing. There's just a lot of parameters that affect the lighting in the room and, you know, other angles that affect how resolution appears for the human eye. But check out that video later after this talk. It's pretty cool. Right. So for reference also, I mean, this is about our phones that we have. You know, an iPhone basically 16 plus has a resolution of the following setup, whereas an older one has much fewer pixel resolution. But now sort of resolution maybe makes more sense, right? In order to compose an image of an older iPhone, you have only this amount to play with to compose a cat or yourself or a selfie, right? Compared to other high pixel resolution. So resolution is critical. But the question is also, do you actually need all the resolution to capture the process of interest? I mean, we saw the deforestation process that was unfolding. It was a 30-meter resolution. You know, the patch size was very, very large, but it was enough to actually capture that process. Right. So there's this paper by Burke et al. And I believe it's in Nature, where they sort of compare the same scene. In Africa, like how would you represent it if you have a nightlight image, a Landsat, a Sentinel, PlanetScope, and digital globe? It's pretty hard for you to see like from this PowerPoint, but if you look at the PDF, you see the markedly difference between how resolution sort of affect the appearance of this information. Right. So who collects satellite images? We mentioned the European Space Agency. We mentioned Planet Labs, Maxar, NASA, obviously with NOAA is sort of the key for Landsat, and ESA for the Sentinel program. And then we have, you know, the satellite industry. Earth is really exploding. There's a lot of satellites out there. We know, I mean, you've heard of this SpaceX, obviously, in terms of its products. It's not doing Earth observation as far as I know. It's basically satellite linkages, full stop. But there's just a lot, especially in defense, obviously, to acquire better edge over your competitors. Right. And also just the notes about like to your question about like the basically why now? Why do we think planetary causal inference and remote sensing for social science in general would take off? I mean, you see the availability. If you look at for example, in Africa, the number of pixels available at higher and higher resolution, this basically has gone up the last few years here. And also the number of satellite providers with high sort of sensory resolution has just increased markedly in the last couple of years. A note about Landsat, and that's sort of a note that is important for our project in particular, is that Landsat actually is only one satellite usually that is orbiting the planet, and it goes back to 1972. In terms of satellite technology, Landsat 1 to 4 is pretty much similar, and then there was a jump in terms of how well the resolution in the bands that they're capturing. So 5 up to date, which is Landsat 9, are pretty comparable images. So you can work with those images without any major sort of technological difference here. And in terms of the bands that you get, I mean, I mentioned the different bands that you have in Landsat 5, the thermal mapper. As you see from Landsat 5, actually what we have is a panchromatic band. I should say all of the resolutions are approximately 30 meters, but the panchromatic band is 50-meter pixel size. So it means that there's a grayish band, which with an algorithmic processing, you can actually increase the resolution of the red, green, and blue band to approximately 15 meters, which is pretty cool. Okay, so challenges in collecting satellite images really sort of pertain to mainly, you know, how the satellite is sort of interacting with the sun and the Earth, basically the atmosphere itself. So if we think about this being the satellite orbiting the Earth, this is the top of the atmosphere, and that's the surface of the Earth. I mean, how does the measurement happen? Well, the key thing is that there's a sunbeam light sort of coming through the top of the atmosphere and then reflecting back through the atmosphere to the sensor of the satellite. And in that process, obviously, things can go wrong, right? There might be interference from space in the atmosphere and so on that could affect the quality of this measurement. But the cool thing, and I find this so mind-blowing, is that there's this digital number, which is sort of an algorithmic pre-processing of where there's a recording of the quality of each pixel in the NASA databases. So you actually are able to sort of to know, where the quality of if there's a lot or less cloud, or if there's more or less reflectance and so on. And that just makes obviously this work much easier. So there's a lot to be said about this process, but just to give you an intuition that there's stuff happening here, and I'll show you a couple of slides in terms of like how the example of sort of availability plays out in Africa from 1986 to 2020. So green here means, so what we did here in this exercise is basically just the exploratory data analysis, where we go into the Google Earth Engine, where they have stored all the NASA Landsat images. So Google Earth Engine is one sort of data storage facility for several types of satellite imagery, where they sort of add up their sort of computational facilities on top of the available satellites. So we ran it there, and then what you see here is that basically green is an example of all pixels being clear to go for analysis. So what we did then is that we went back 30 years for the whole continent of Africa and analyzed each pixel through that digital identifier to see, like, could we use this image in our substream analysis. And what you see here is Algeria, and black meaning there is no images, and red meaning that there is image. Sorry, this is no pixels. Red means that there is pixels that is of lower quality. Basically, there's some kind of an interference. And so it's still pretty good to go, but it'll be hard to, for example, say something useful in Algeria here in the south, 1992, for example. Right? If you keep on going, not so good pixels. What you see here in Cameroon and the 90s, clearly something is happening, potentially even systematic, actually, interference here. Yes? Yeah. So this is basically what we're doing, is that for each year, we're going in and are basically checking, is there a pixel in this year that we could have used? Yeah, exactly. So basically we go in each and every spot. I mean, I don't remember exactly how many billion pixels we're checking, but basically asking within this year, in this area, like imagine this little corner here, is there a pixel I could use? And then I go in with that year and check, no, there isn't. Then I return black. Yes, there is, but it's patchy, I give you red. Yeah, because it could be multiple pixels. But if it's black, really, there isn't anything. And then it keeps on going. I just want to show you a little bit that, great stuff, but there is some issues here to keep track of. And this is basically just summarizing what you saw at the pixel space, a proportion of available pixels. So what we saw in the first slide, a Bay Area is basically all good. And then we have some other areas where it's pretty bad in the 90s. And so we go here for a country. We do like an aggregation of the whole continent, and we indeed see that this is not just one or two countries. There's something more systematic going on. So yeah, we have this. I have the slide in my lecture, so I have to ask you here, what's going on? What do you think? Give me your best guess. Exceptionally bad weather, what's going on? You're on the right track. You're right on the right track. There's something human, at least. Something with governments, definitely.
A lot of pollution, perhaps. Like, I'm from the LA area, so I think
Yeah.
smog layer.
Right. Not really, but good guess. There is an interaction, but there's no Soviet in it. Anyone else dare taking a shot? it's something human, definitely governments, rules, or yeah, well, let's just do this. Era of privatization. So the US government decided to privatize this endeavor and said, like, we'll just release pixels and images that actually sell. And so what it meant is that they basically destroyed images that weren't the market for. And then the French, so this basically was dominated by the US at that point, and they said, like, hey, we can probably sell. And then the French came along and some other countries started to launch, and they say, okay, so there's probably no market for it, but it's a public good. So we'll just basically buy this whole thing back, and then we launch again, and this is it. Yeah, that's what you get. So yeah, so that's one thing that affects us. Another thing was that Landsat 7 had a malfunction on one of the sensors. So this is important because Landsat was for a time the only one and well, was planned to be the only one in orbit. So this looks good, Landsat 7, and then it malfunctioned. So this was bad. They tried to fix this in many different ways, but they failed basically. So what this means is that yeah, I mean, this is like basically a sensor failed, so stuff happens still. I just want to say, satellite images are not perfect. They're great, but there is stuff that you need to be worried about still. Great. So to the first part of the just basically showing you how you import images into our studio, to R with existing packages. So much of these, I should just say, this part, I feel like there's nothing particularly special about what we are doing in here, except for that we've been discussing and potentially creating some kind of a, if you know R, there's this sort of tidyverse of multiple packages interacting in terms of visualizations and modeling and so on. So there are existing packages doing a lot of the stuff just seamlessly and nicely. There's still potentially a need of creating some kind of a package on top of it that make it interact with the causal images package in a nice way. So at your free times and interests, just click these links. They take to existing tutorials of how to actually work with these data sets, from Google Earth Engine to fetch images to European Space Agency, such that you could actually play around with that in a nice fashion. So loading images. Let's just if there are any questions, I'm happy to take them before I show. All good? It's hard to read? Okay. Let's change the templates. Should be global options, I guess, right? It was a while I changed this. Should be in the appearance. It should be, which one would you prefer? This is better? It's better? Yeah. Very cool. So it's just a few line of code. So what do I have here? Essentially what I have, I'll be using the raster package. I mean, this is a very established package where basically it handles raster files. Super simple, nothing fancy. Just for those that haven't played around with image data in R, you can basically, and I'm going to show you this little file that sits on my computer. And I'm going to load this Cairo PNG, which for the sake of just fun, I actually had O3 create a map, an image of Cairo for me. But it's an image, okay? So, and it has 3 bands. That's the most important thing. I was debating. Landsat looks good, but it doesn't look as nice if you don't have higher end computes to load it. So nonetheless, it just is on my computer. Raster has this very simple loading function where I load this as a brick type. It's an image object type that the raster package understands, and then I'm gonna basically just plot this as if I don't know how many of you have actually seen images in R, like actually plot. Yeah, we have 1, 2, a couple. Okay, so some people. So it's actually always for me when I loaded the first image to R, I was like, can R actually read images? This is freaking weird, but it does. Like, that's an image. Okay, so I just wanted to give you that intuition that you could actually load images into R. It looks pretty good. And so you don't need to use any other software. So what does it says? It's actually a 1024 by 1024 pixel size. So again, going back to our intuition, essentially there are 1024 pixels here. Okay, each and this array, what you see is it looks two-dimensional to you, but it's actually a three-dimensional object, and there are 3 bands in the background. And those 3 bands, when we call this object to be plotted, we call those array identifiers. They call 1, 2, 3, and we do have to call them in the correct order, I believe, Marcus, right? When we call them in the wrong order, they look a little bit convoluted. Because I was always wondering, why is that the case?
Why the red, green, and blue?
Yeah.
I mean, it's, you capture the intensity. So if you take a picture of something blue, then the blue band will be very high intensity in that specific pixel weights. And so if you render that as red instead, then the image would look inverted, like the blue sign would look red instead. So
I see. Okay, so this is kind of predefined slots.
Yeah.
There we go. And yeah, you can obviously like nullify one of the bands, and then you can get a non-red banded image, if that's a word. Right? You basically have only now green and blue to plot this. And that's it. So I just wanted to give you a takeaway. You can actually handle images in R, and you can work with them as any other image object. You can go into pixels and manipulate those pixels and nullify them, redo them, and so on. And what we will be doing actually in the coming parts of the script, when we come to the causal inference part, I'm going to draw you an image. Actually, I'm going to create an image and create houses. And those houses would be correlated with the confounding in a particular way that will be important for our causal analysis. So that's where we are at. And I would like us to, if there's any other question on this, and potentially break would be a good place here now. But questions, please.
Sean, the African, like a yearly satellite images, like for each country, for example.
Yeah.
Yeah, and then my question is that if we're going to use it for a kind of research analysis based on this yearly country level analysis, then what if a country has more than several images? Then what image you are going to choose as the yearly image?
Yes, so this is part of the critical, what I would call like hyperparameter selection for your research project. So it's unclear, it depends on the process of interest. So take, for example, the poverty examples that we work a lot with is that you might argue that within a year, I have all 24 images available. And it might say, living conditions might not improve that quickly. So therefore I select one image, and I might select, the medium pixeled image. So I take all the 24, I take in each pixel the median, and then I can select that as my image representation.
Like you don't have to choose a particular one. Instead, you can just merge them.
Yes, exactly. So that's that's sort of what I would call like the temporal of summarizing images. How do you think about image summarization? Do you take the mean? Do you take the variance and the mean? Do you take maybe a kernel? Maybe you don't take in each pixels. Maybe you do like in every 4 pixels you summarize, right?
But I'm interested in this like data preprocessing part. So are you actually doing something for data quality, like for example, cloud coverage?
Yeah.
It's exactly in this particular case, I'm just curious how you deal with it. Like you have basically several images per year, and if you're doing this mean, then what would it be basically like? Are you selecting? Are you doing like quality checks or like in an automated way, or are you manually adjusting them? Or
No, this is part of the key questions that held back one of our first publications, which is like thinking about like processing for clouds, for example. We had this paper published in the International Joint Conference for Artificial Intelligence, ISCAI for short. The problem was, how do you handle those black images in Cameroon, right? There were years without any available image. So what we had to do is basically do like a 3-year median. So it wasn't enough to do within a year. we had to basically go 3 years to find 1 pixel that was sufficient for that size, at least. Yes, I mean, you could do a pixel, yeah, you could do a pixel imputer. I mean, there's definitely ideas around that, so you can impute pixels. But the problem with that is that you have to train a model, you know, such that your imputer actually, you know, is yielding correct results. But I would say there's no easy answer to this, because it really is dependent on your domain and how important it is to capture the process quickly. So, for example, for the idea that taking the median over a year wouldn't be a good idea if you're in conflict research, for example, right? Which you are. So then in that case, the problem there is that you're not capturing a slow-moving process. You're capturing a fast-moving process. And if you want to figure out what's the effect of war on, say, living conditions, well, then you want something that is able to pick up that change very quickly. You know, if there's an army invading this city tomorrow, you know, it will have a marketable difference on living conditions the day after. And you want to, if you want to brand this as a sort of a measurement process, then you want to measure that process as fast as it happens. So what do you do then? I mean, this is hard. I don't know. I think it's part of the research actually to figure this out. So if you have ideas, I'm happy to indulge them. Yeah.
Thinking so seasonal effects too. I think there might be a seasonal effect. I deal with that a lot in my research. If you're looking at poverty in Africa, for example, especially like sort of tropical Africa, there's 2 rainy seasons, 2 dry seasons. So
Yeah.
those might affect if people can get goods and services.
Exactly. Yeah, that's a great response. So basically, if seasonality is important, well, then basically you might need 4 representation. Maybe you do 4 images, right? What kind of research do you work?
This stuff actually, I work in veterinary medicine, but I work with like how people respond to government actions for preventing disease. So this specific image stuff I do is sort of unrelated to social.
I see. Okay. Yeah. So thinking about the question is critical, like the process and the movements of the process itself. Please.
So if you use the yearly data from year to year, and what is your dependent variable again?
Yeah, so in our case, I mean, that particular paper, I mean, we have different papers, but that particular paper that we're talking about is health and living conditions. So basically, think about it as a material wealth index of number of televisions and bicycles and the quality of water and so on that characterizes a household.
Control for confounding events like wars or fluids, which I think has sadly been the case in many areas in Africa.
You mean when images aren't available, or if
don't have a linear evolvement?
Yeah.
That puts in a breaking point.
Exactly. So what I'll be showing you is mainly using 1 slice of an image, but you could actually use the whole temporal sequence as, if you believe that, you know, there's some dynamics happening and that dynamics is represented in the image space, basically how maybe a city is growing, or talking about the mine examples, like the number of mines that might be located nearby or whatnot, but also the way that process is unfolding, not only that there is, but also the unfolding process. Then you could include a video of that as part of your confounding set. So you could basically say, I have this study in, say, in the 2000s, and then, but I'm going to say, like, actually in the 90s there might be stuff unfolding in a particular way, so I'm going to, you know, use images from there to use that as part of my adjustment set. So that's possible, and it's also possible within the causal images function setup right now. Yeah.
I thought you did the temporal analysis, but you did like you did just a causal model for like one time.
Yeah, we could do both. We could do both. Yeah, we could do both. But we can talk about the details after. I'll be happy to talk about the study you're interested in. Yes. Very cool. Any other thoughts, reflections, questions? All right. So in that case, let's take a break. Thinking that if coffee is served in 45 minutes. Let's do like, shall we do 15 minutes, 10, 15 minutes, 10 or 15? Who wants to do 10? 15? Okay, more 15. Let's do 15. So let's do, so we 10 past. Okay, good. I think we need to start. Great conversation. Good. So what did we do in the first part? We walked through what images are. We talked about satellite captured images. We imported one simple image into R. For some of us that haven't seen R actually being able to plot images, that's a sort of a wow moment. And now what we're going to do is to head into the causal inference step. So basically thinking about, great, so how do I work with image data? And how do I think about image data entering my pipeline? So first, I just need to, not the video, not this one, floating menu. Okay, there we go. Connor, you can hear me well, right? Great. Great. So just some basic definitions of what we mean by causal inference here and what is our target of interest. So much of applied research is about understanding cause and effect, right? So like we talked about the idea of building a road and potentially what's its effect on poverty or health and living conditions in a particular locality. And then we also said potentially there are, some confounding, and we took the mine example that, people tend to locate when they're potentially mines, and that might correlate also with the actual living conditions of that location. But nonetheless, it's still our target. What we want is this sort of average treatment effect tau. We want to sort of summarize this arrow with what's the sort of average effect of X affecting Y. So in observation studies, we wouldn't be able to randomize. So now in a non-random randomized setting. So what we would need to do is basically to think about ways of conditioning. And then you might say, hey, but I might have IVs. And yes, you might have, and you might still have conditional IVs, meaning that might still be confounding that you want to condition away with. So all of this sort of applies still in a general sense. So what do we do? What does C actually do for us? So the thing is, in this unobserved setting where it's circled around, meaning that you can't actually observe it, you would be biased, right? So you'd be biased because what we mathematically need is sort of averaging over this expectation of C. We want to observe all instances of C so that when we have this big joint distribution, we would calculate tau in such a manner. So we have, I'm going a little faster potentially. Potential outcomes framework, who knows a little bit less? Yes, and DAGs, directly the cyclical graphs, a little bit. Okay, cool. So just a very basic definition. So essentially think about, for those that are new to this sort of causal inference definitions, is that think about this as being a joint distribution between X, Y, and C, right? So we have this joint distribution here. And what the true conditioning, or the factorization, I should say, the true factorization of this joint distribution follows that definition, meaning that C happens first, then conditional on C, X happens, then conditional on X and C, Y happens. Okay, this is sort of an unfolding of the world, right? And research, what's research about is try to figure out these joint distributions. What God or whoever did this to us, put this in this world, what kind of process generates this world, right? And then if we're social scientists, we want to figure out in our particular domain, what's this joint distribution looking like? And ideally, that's what we want, but it's sort of very, very difficult. So we end up, talking about certain parameters that summarizes this joint distribution in some useful way. So causal inference is really sort of committing to the claim that X actually generates Y in this mechanistic way, right? That we have sort of unfolded this joint distribution in a faithful way, meaning that it's sort of faithfully representing the causal process of interest that we don't observe, but we are hypothesizing about. Okay, and so in this perfect world, there are only 3 variables. Obviously, in reality, there are millions of things happening simultaneously. So any observational study will be a simplification, but we are fine with simplifications, but because they're better than random guesses. And science is trying to do sort of educated guesses. And the better science, the better educated guesses. And that's sort of the process we're at. Okay, that's sort of how I view science. Anyone disagrees, please feel free to raise your hand and disagree. Okay, that's causal inference. Statistical causal inference is trying to represent this in actual mathematical objects, right? That is able to discern these processes in a quantified manner. So in order to actually figure out this tau effect of how X is causing Y, we would want to observe instances of C, right? In order to do this calculation, because we're, again, doing the summarization over C. Now, this is potential outcome notation, just basically saying, like, technically, when we do causal inference, we would want to, one way of characterizing this big joint distribution is that mathematically is just to think about like me imagine this X being binary, right? So I live in a neighborhood where there is a road and there isn't a road. And then I want to figure out what's the effect of that on my outcome, like my wealth level. Okay, if I live in a neighborhood where there isn't any roads, which there isn't in many parts of the world, so it's not an unrealistic assumption. So I need to then figure out basically myself, if there's an index I, like what would have happened to me under the world when there is a road and there is under the world where there isn't, right? Ideally, I want to observe these two jointly, and obviously that can't happen. It's not possible. So the whole idea now is to figure out ways of making these parameters identifiable, and the way that we do that usually is to assume some kind of a comparability of units, so that I can't observe myself in 2 instances, but I might be able to borrow information from you. We might be so similar in the space of C, such that we are sort of, the way we would be confounded would be similar. So, and then we can see the rest of the units being similar in that very systematic. We have a sample, and then we can sort of aggregate. So the hope we can make is to find ways of making ourselves comparable. I'm making this sort of a kind of a high level, little hand wavy summarization of what potential outcomes are, but essentially they map on to these quantities of interest that we want to measure. But for the sake of this workshop, really, that's not the potential outcomes definition is not that important. The way I want you to think about this is more in terms of causal systems, and what we want is to represent certain variables, random variables in the system that we can't measure sometimes directly. Okay, so that's more important for you to remember. So these arrows here are directional, meaning that they do have a causal effect. That's sort of the idea. If this would be a non sort of what we call a cyclical joint distribution, like statistically, I should just say, actually, this is important. So this is the true causal factorization. In statistics, like you can factorize in any way you like, right? Like, I could start with X and do whatever I want. But because there's a stipulation of the way that the data generating process is happening, there's actually only one true factorization, right? And that's one that we're trying to get at. The thing with social sciences, which might be bugging, is that all the social theorizing happens at the level of how these DAGs should be structured. So that obviously is fallible, but that's the game of science, that we're trying to, through interaction, come at better and deeper representation of the world. Okay, does this make sense for giving you just this intuition? If not, please raise your hands, and I'm happy to go a little bit deeper onto this. Okay, cool. So we basically, obviously we want something unbiased, right? But I just told you that sometimes, when the data is not available for us, and there's a lot of text here, but essentially you can think about ways that we can potentially proxy certain variables here, certain variables that we don't observe in this particular manner. It's C that I'm going to target. And what I'm going to tell you is that if now we can't observe C, potentially we can produce a proxy of it. And a proxy, you can think about being an imperfect representation of that variable that we wanted to have but cannot observe at the moment. Okay, and so here there is basically a lot of literature on proxies and drivers. So there's something called proximal causal inference. Sort of there's a general approach. There's a bunch in text. Chen, I think, Katie, you've been on this in this paper here. In your lab, we've been working on a bunch in image data, and like basically this workshop is about thinking of images as proxies. Okay, that's sort of the way that we enter this game. And there is, I should immediately say, if you don't want to if you're not willing to make assumptions about proxies, you can go in another direction, which is to bound the effect. Say that, hey, okay, so I don't observe C, but I have some sort of Bayesian priors about how strong C is. And so I'm going to give you like at its lowest and at its strongest, I'm going to give you a bound for my causal estimate. And that would be like the best you could do if you don't want to actually measure C in some other direction. But this proximal causal inference literature is saying, hey, we can actually do better than bounding, and you can potentially leverage multiple sources of information of trying to sort of isolate the effect so that you arrive at something unbiased. I'm going to do sort of a less of a stringent call, meaning that I'm going to say, as long as we're doing better than not measuring C, we're better off scientifically. Okay, that's sort of my stance. So what does that actually mean here in our particular setting? So in this proxy literature, often what happens is, again, you want to measure minds, this C variable that you don't observe, but you potentially have text documents describing C. Like the World Bank official says, okay, so where should we place this road? It's not that they talk about roads like that, but imagine that they did, okay? They talk about like, where should we place it? Well, we place it, maybe where people need it, but it would be good if we could place it here closer to this mine that U.S. interests are serving in this region. So that'd be easier to transport certain things from this mine to the harbor. Okay, so that might actually stand in the documents. And so you could use text. You could use text to proxy C, because now it gives you information about the placement of these mines. But you could also use images, right? You could use images, as I argued earlier, that these images might give you information about the placement of mines. And so you might not have this sort of confidential information about how the World Bank officials were reasoning about the politics of roads. And so you have instead satellite images. And then that would give you a similar set of information about where C, the distribution of C over X and Y. Is this sort of making sense? Okay, so it's a bit of a storytelling here, but I want to give you intuition more than like giving you algorithms, because like at the end of the day we can do this in many different ways than at the algorithmic level. But intuitively, as long as we're on the same track, we stay focused on the same goal, we'll be sort of achieving that goal more efficiently. Now, there's this paper in ICML published last year called the Platonic Representation Hypothesis. It's sort of a fancy term for something relatively simple, but it's a cool idea. I mean, here the idea is that basically it's saying that imagine you have the world as being Z here, these cones and spheres and whatever, and that they can be represented in image space, some kind of a sensor, satellites potentially capturing it and then encoding it in one data set. Or you have some other process, like in text, potentially capturing that in an archival version or whatever, creating another representation, right? So X, Y, and Z here don't map to my causal system previously. It's just taken from that paper now directly, okay? So what is this saying? What they're saying is that there's potentially this hypothesis basically saying, hey, what if these modalities are actually converging to the same information space? In the perfect world, in my example, this archive of World Bank chats and strategizing in text yields the same information about the placement of roads as satellite images do. And if that's the case, there's this sort of convergence of information, right? So basically saying it doesn't matter if you use text or images, you would achieve the same goal. Now, would you believe that? Who would want to argue against this? And what argument would you leverage? I have tons of arguments to leverage against it, but exactly, distortions and different perspectives. Like, you know, I would say you'd be hard pressed to say, hey, all the world, this big joint distribution could be encoded in exactly the same manner. Now, I would say not the same way, but in the same manner, such that images and text would capture them exactly. I think that's right. That's at least my position. So there's maybe not convergence. Maybe there's a convergence to some extent. Maybe there's rather complementarity. Like, you know, why do humans need 5 senses? Like, we could maybe do just one. I mean, if this would hold true, we could just do with sight, and then because we don't need to hear, because images, like just seeing, would do the same thing as hearing, right? So why do we hear? So there's clearly something else with that sensor, you know, compared to imagery. Okay, but it's a cool idea. I think it's a cool idea because it gives a perspective about what data is, and ultimately data is some kind of an encoding of reality, right? And the questions that we need to ask as scientists is that what encoding is happening and in what information space. So even if the hypothesis necessarily doesn't hold true, it gives you an idea about what is my data doing for me in my pipeline. Scientifically, you know, where am I in this joint distribution? What are images, text, tabular data doing for me? And can I create something new that helps me unravel this tau? That's my story. That's the thing I want to get at. Please.
My own
Yeah. Yeah. Okay. Yeah.
I also think, like, assuming missing at random is not good for stats.
Yes.
They're almost never. Where it sounds like with weather, maybe you can assume missing.
It's a very good point. Yeah.
Exactly.
The satellites, yes, I would say so, except for like the 90s that we saw in the privatization area. There is definitely not missing at random because its missingness is a function of willingness to pay. But otherwise, it's definitely missing at random due to clouding. But we also know that clouds is a function of environment and climate. So we would know that, I mean, if you Google and see what's the cloudest area on the planet, Iceland would be one of them. And I think there's another one somewhere else. And what's the clearest place on the planet? I think it's Chile somewhere on the mountain. So then satellites would work better there. But other than that, it's not missingness. Maybe we should call it like missingness at random, not due to human interference, right? Because that's where the bias will start to happen. If we're after to analyze social systems, if it's environmental systems, obviously then environmental processes will matter more. Okay. All right, so we're on the same page. Great. So this convergence, as I said, will only happen if there's like a reason for it to converge. I mean, again, like as I took the example of biological units, you know, there's a complementarity of senses, and then potentially we should think about these. I would suggest that we should think about these as a complementarity of data sources and modalities. And then the question is, how do we integrate them in a sensible way? And sensible would mean algorithms, involving algorithms, but in a way that distills down the information you need in a distilled way, in a sort of disciplined, systematic way. But that's the whole trick, right? That's the whole trick in causal inference is that even small distortions, if your tau is small but very important, and you distort your signal such that you think you're proxying C, then you'll likely be off, right? And so how do we know that? How do we think about that bias? That's why measurement error becomes so important here. I mean, it's such a boring topic, you might think, but ultimately, it's probably the best topic ever because if you have something very precise, you can measure it and it's important, then you can do stuff with it. So I have this piece. I'll obviously do some advertisement for it. It's in Harvard Data Science Review, where I think about like the ways both the predictive side and the causal side play a very, very important role in intermingling together as a way of also like I don't know how many of you have read this piece by Brayman, the two cultures. Right. Okay. So here I'm playing on that word. I'm calling this a third culture, which is actually the synthesis. Like, how do we think both predictively? This is where the machine learning, deep learning, and all the CS stuff, language come in. Like, it's the algorithmic modeling culture. We don't care about tau. Like, I want to predict y. If I can predict y very well, like why do you need tau? It's like, but that's the data modeling culture. We care about that tau because there's a scientific process that we are interested in, but both are right in their value. Like I could be caring about predicting y, and I could be caring about distilling tau in a very precise manner because they're complementary. And then so this piece is arguing for how they're complementary and arguing for the hybrid modeling culture instead. So that's that. Okay, so let's focus on satellite images. But I think I made the point here that this could actually be anything, right? Text, image, audio, they can complement each other. And especially if C itself, I mean, now it's very it's represented in a simple way, meaning that it's just one random variable. But you can think about these C's being a vector of random variables, and then you might be serving them, proxying them with different modalities, right? You might have C1 with images, C2 with text, C3 with audio, C4 might be observable. So there's nothing hindering you of taking this to the limit. But let's think about the way that we think about imagery, particularly, because this is, after all, a planetary causal inference workshop. But I want to open up your minds for it, that there's a broader perspective to be taken. So we are, and the classical backdoor confounding, this is just basically taking an image, and sorry for the notes now being X is being A and C is being C. But from that, all the errors are maintained. So essentially, if you're in a classical backdoor confounding setting, you want to measure X and U to do this. But now we're going to ask, how do we, M now being the image, how do we devise a function such that it retains information about you in some useful way, right? And the hardest setting is that when you have no information about you. But in the simplest setting, you might have some information about you. You might have some annotated examples even. And that means that you can dramatically increase your movement or action space in terms of how you can isolate that tau effect that you're interested in. In the original paper, I mean, all of this function, you can think about this function as being basically both my image processing and the modeling step. Meaning the image processing is basically all the questions we discussed in part one, like your question, oh, should I take all the images? Should I use this pixel, that pixel? All of those choices potentially will affect your ability to proxy you, okay? Now, I'm talking about this in the general, right? But there are ways of checking whether there is information towards you by, for example, having some annotated image data. But ultimately, I mean, again, I just want to go back, like, how would you, as a slight divergence or from the main line of ideas, is that how would you, as a footnote, characterize the measurement of y, like the poverty example that we discussed just now? Well, there, instead of doing the function of u, it's really y that is unobserved, right? And you have something like the following characterization of a DAG. So in our setting here, what we're saying is that you have some variable y, and then you have some potential other variables, including images. Then you can questions, can you devise an algorithm now to measure y, right? So I just want to basically show you how you could play around with this idea to potentially do any of these key variables such that you want to sort of extend the pipeline. Okay, so So this seems very useful. But what, and this goes back to your question earlier about like, what is images then providing? Like, you know, how is there a general framework I can follow in terms of what confounding could be? How should I think about it? So this table is giving you a summary of our framework here. So what we have is in the columns, we have let's begin with the columns. Yes, we have observable image features and latent image features. So basically say confounding can be observed in the image or it could be latent. And what are we looking for? If it's an image feature observed and it actually is in the image, like what example can you give me? Well, it could be, for example, solar panels in a farm or the amount of forest, stuff that you can actually see and a human eye would recognize, like this is a solar panel, and this is a mine. And what would be what we call connectivity? I mean, now we're borrowing a bit of concepts from network science. But if you think about like what an image is, in a way, it's sort of an arrangement of objects. Like, you know, I might have, like if this is an image, you know, if this is an image, you see my little, is this possible for you guys to see? I guess it is. If this is an image, like I might have forest up here, you know, and I might have like houses down here, and I might have a road here. So, I mean, naturally, this would be a connector, but if you think about it, it's also the placement of forest in the image is in a way designating the way it connects to houses spatially. So spatiality is basically a continuous space of an edge, if you like to think about it. And in fact, that's even how you model spatial analysis. You have an adjacency matrix, same thing as you have in network science. And then you think about some kind of a kernel of how close they are, such that if they're within that kernel, then they get one, meaning that they're connected. So that's what we mean by connectivity. It's basically the arrangement of different positionings in that image. Now, the latent image feature is interesting because that's where things like become a little bit how you say. You can start sort of squeezing in stuff that you can see, like potentially it becomes like everything because it's latent, right? But that's interesting still because we observe to some extent, to a large extent, at least in the wealth inference idea, that you can use these images to predict wealth. And so how would basically this play out for the connectivity idea? Well, this could be also that sort of the relationship inferred from the image setup, so that the way that these two connect might not be exactly in the visible space, but it could be in the representation space of how features are extracted. It sounds a little bit abstract, but think about it in terms of like an embedding space. If two things are close to each other, they sort of are related. That's what I mean, like literally that. So it's some kind of a feature space where they're close to each other, so therefore they are related. So it's now not relatedness in the visible space, but in the latent embedding space. So what does this mean in concrete like practice? Like especially if you compare to classical confounding adjustment in spatial analysis. So imagine that you're in this particular space of the slide where you have two time points, 0, 1, and then I'm hypothesizing basically that, you know, I'm testing for the effect of railways, you know, in this example, and so there isn't any railroads here, and then there is, and so what do I do? I basically collect or annotate manually, you know, the location of the city. I collect, you know, the population size. I might collect, like, you know, I need to collect the GIS coordinates and, you know, all the fun stuff that you do with tabular data. And then not only that, you need to do it over time. But so what would like an EO driven confounding adjustment look like? Like, I mean, this is an image, right? I mean, it looks like it's a hand-drawn image, just trying to show a point here. So imagine this is actually an image, like this image, but we drew this by hand to show you. The point is that there's more stuff happening in the image. I mean, even if you had the road data like this, it would basically do an Euclidean distance. I mean, you could do more complicated, but it would become very expensive very fast for you. But in an EO-driven, I mean, if the image is of that sufficient resolution, you actually see the shape of the road. You'll see the road, you see the shape of the road. The shape of the road might have a particular setup because there's a mountain there. And that mountains wasn't in your data because you didn't think mountains were important. But in the image, you actually have that. And you did in the classical setup collect, annotate, mining data. You did. So that's good. But the type of mines, the shape, the way that they might have grown over time, like it might be tons of characteristics of the mining place that your tablet data didn't collect. It's basically a lower dimensional feature space such that that might be important for your model. I'm not saying it is important, but it might be important. So this is like the game of observational studies, is that it might be important. So you end up like adjusting for billions of things, and reviewer says this might be important. So now you could at least say it might be important how the mine shape is and the road shape is, and I can actually include it in my EO-driven confounding analysis. So you see the difference here, the intuition? Yeah.
Like in the previous slide, you mentioned about the analogy with the networks like nodes.
Yes. Yes.
It's like a metaphor, or you're also trying to model it like.
No, it's a metaphor.
Oh, okay.
It's definitely a metaphor.
Because I'm wondering, like,
Yeah.
slides, if it's really going to be a network.
No.
The
Yes.
nodes are going to be like several types of.
Exactly. No. Got you. Very good. No, it's a metaphor. It's definitely a metaphor. It's the best metaphor we could come up with. We've been like thinking a lot about how does confounding come in an image space, right? And what does it actually do? And the best metaphor we've come up is through network science. And essentially, I should say, I mean, potentially this table should actually have one other dimension, which is the arrangement of objects. So in networks, you don't necessarily have an arrangement question. Like you don't have, I mean, you do have spatial network analysis. I think that's sort of the closest that you would come to what I would call classical confounding adjustments. Sort of not only do you know which nodes you will have, you also have the GIS coordinates. You can place them in space. But rarely would you in network science actually have also space data about like where to place the network. So the network can have many different shapes. Whereas in EO-driven, you have both, if you like, the ideas of connection and nodes, but also the arrangements almost naturally appearing in the image, right? Like, as I said, in the forest and the house, the mountain, the railway, I mean, the ways that the things co-locate. So this now gives you sort of a new dimension of potential confoundings that you could control for. Yeah. Any other thoughts, reflections? So yeah, please.
Feel free to punt on this because it might not be.
Go for it. Yeah.
So what you're saying is like embedding space, the representations are close enough together.
Yeah.
That you think you can adjust for things that are similar in semantic space, but not exactly the same.
Yeah.
But if you're actually doing like an applied project,
Mhm.
right? So you don't have ground truth data because it's observational causal
Yeah.
inference. You're relying on this assumption that like the representations are put in on.
Yes.
Like, how does one,
Motivate that. Yeah.
Be not concerned that like one or both of those pieces something could go.
Yeah. I mean, it's a really good question. I should say, like, when you're basically in this latent image feature space, I mentioned the literature of causal representation learning. I mean, they've thought a lot about like how the representation space sort of can bias your analysis in a particular way. So I would sort of, to some extent, defer to that literature. But I'll still attempt of saying the following. I mean, what makes me optimistic that things might not go wrong is like as long as you are not committing post-treatment bias, if you're sort of pre-treatment images, if they matter, you know, say in your propensity estimate. Okay, the battery is low on this, so let's see if I can connect it to. Give me a moment. And I cross my fingers it will work without the receiver, which has. Oh, actually, Connor, can you hear me now? 1, 2, 1, 2.
It sounds great. Works.
Great. I just had to plug it in. I thought it should go for 20 hours, but I was clearly wrong. Okay, let's sit this down. And then where is it? Floating. Okay, great. So where was I? So, okay, now this guy died. Right, so it wasn't a question on this, Marcus? No, okay, all right. Yes.
Question, I'm not sure I understand what I think, but like, is there one more? Is there like?
Yeah. This is one example. This is one example. And next time I'll put up which value it is for this particular neighborhood, just to let you know. But it was just an example of like, you could actually, this is quite interesting that you could have values in each pixel of what label it has. You can have values for the whole image of what value this image has. Well, that's like the key intuition that I wanted to give you here. And not only this image, you can actually have this video if you like, right? This sequences of images can have one value. And that's sort of the flexibility of how you merge different modalities together. Right, and what I want to just basically emphasize, what I've probably already emphasized, is that non-annotated images are very useful still, as I argued here. So this is just basically showing from a sort of a agglomeration literature where you can think economic geography. Basically, you think about where positionings of industries, how they sort of co-locate and then intermingle and then create larger and larger blobs of industries. And that, you know, you can again have annotated or non-annotated. The mine example, you might say, like, you know, you overdoing this mine example thing. I might be overdoing the mine example thing. This is Chile, and this is an open mine, 1984. Let's see if I can play it again. So if you focus on the certain areas here, you see that, you know, there's actually a lot of, like, we have deforestation, but there's mining, you know, of mountains that you know, have a certain effect on the visual spectrum that is important, or likely is important for the analysis at hand. Okay, cool. So this is great. You might say, I'm convinced this is good. How do we actually incorporate this in statistical analysis more hands-on? So I'm going to give you one example of a paper that is currently under review with World Development, and that we wrote with Cindy Conlin, who was a student with us at IS, and now she's in the US working for a software company. And she did some fantastic work on basically taking all the data that we have for Africa and merging it with World Bank and Chinese programs data. Basically, those are tabular data that we have other teams annotate, and then we have our data set that we use that Marcus created, and also the DHS core, the labels from that region, so that we can compare the results with and without the predictions. So the setup here is essentially just a very quick one. Is basically we have an outcome, which is this, what we call the International Wealth Index, the IWI. It's measured at the household level. We have these World Bank data set that I mentioned. And here, you know, the whole game is to try to deconfound. And you can use instrumental variables and so on. We have some of that in there, but the key thing that I want to emphasize here is really, even if you do IVs or regression discontinuities or whatever identification strategy you use, difference in difference, you can use the image space as an additional adjustment. Okay, and then we're gonna use some inverse probability weighting, essentially meaning that we're gonna summarize all the confounding information towards the treatment selection and a weight that we then do a mean difference of. Okay, so, and we are using non-annotated images in this pipeline. So I want to be just very concrete of where does this enter our analysis? Like, be more concrete, please. So here, what we have, basically, what we're doing here is if you look at this probability here, and D being the treatment, so we're going to predict, usually we only use observed confounding, these X's. What we're going to do is that we're going to also include images in this adjustment set. Okay, that's virtually the only difference. Now, that's where images enter. But you might ask, what is this function over here doing? Because this function needs to be able to handle images, right? And that's right. I mean, this is like the whole game. This is where we now enter why this work might be quite difficult still to manage within the existing machine learning frameworks if you don't think in terms of computer vision. Great. And then, once, imagine now for the sake of argument, just imagine we could do this. We basically have a function that can take images, it could take tabular data, and then what we're going to do is that we're going to predict this probability, basically going to estimate this probability by predicting the probability of taking the treatment. So we observe in this location a Chinese program or a World Bank program. Then we're going to use images and other tabular data to see if we can predict that location. What's the probability? Basically, we get a probability of all these estimates. And that is a way of modeling, basically summarizing down the information that images might yield towards seeing a project located here.
Sorry, what's the unit of analysis? Will it be a small town or?
So this unit of analysis, we have two different types of analyses, but think about this as being the pixel only. Right, so we have a 6.7 kilometer square pixel over the whole continent. But you can also think about this happening at the administrative level. So administrative levels is basically a larger of a municipality, basically. So you can do this at any level, but here we did this at the both at the pixel level, and I believe that we did this at some kind of a area of a donut that we basically define for each unit. Okay, does this make sense? Right, so once we have these weights, I mean, these are just basically, it's now just a vector over the units. We can now calculate this average treatment effect, which is now essentially a reweighting scheme by the probability of that we estimated. This is the propensity score, essentially. Right, that propensity score is a low-level summary of a high-dimensional feature space. Okay, great. And then, and just to be clear, like what kind of images did we use? What we used before the treatment happened, -1, so it's the last year's image. It's a 5 kilometer daytime satellite image, basically centered around that neighborhood that we measure. And so again, no annotation. So it's very important because we're doing this at the continental scale. We're using the whole continent of Africa, 30 years, of it, 20 years of data. I think that's where we have the treatment. Okay. Now we have a bunch of different definitions. You don't need to think about this. The only thing I really want you to focus on is that we use images as a way of proxying that C variable in our causal system. And we had a bunch of other covariates, but really the important thing is that we can then create that low-level summary, that weight that we then use to calculate this mean difference between the treated units and the control units. Okay, that's sort of what it boils down to in its essence. It's a mean difference estimator. And then you could use more advanced, doubly robust machinery here if you wanted to. But just essentially, this is the thing that is happening. That's our tau. It's the difference between those that took a program versus those that didn't take a program. Okay, great. So we have many different programs in this data set, but I just want to show you the geographical distribution of the two different treatments. So the blue point are the treated points. It's about 4,500 points. The control, about 30,000 points. And we had a kernel basically that defines within this kernel, if they're within this kernel, but they didn't have a treatment, then they're in control. Meaning that we wouldn't have anything up here because we focused on sub-Saharan analyses. And this is the same now for Chinese programs. But nonetheless, it gives you the geographical distribution of these treatments, okay? So these are actually GPS tagged locations. I should say that they are not on they're basically at the admin level, okay? So when there's a road, it's not that we have the exact vector space of that road, but we know where it occurred and what about the cost of building it and so on. Great. So now imagine we did this and we calculate these averages, and then we did this for not only health that I showed you, but all other types of sectors that are defined in the tabular data. And what do you see here? So what you see here is on the x-axis, positive means positive effect. So basically there was a program and then the effect was positive, meaning that it increased wealth. It was actually beneficial. And what we see is that, and blue are World Bank, red are Chinese programs, that both Chinese and World Bank programs are beneficial. Okay, good news for both of those. We also see another trend, which is Chinese programs overarchingly in this sector was positive, more positive. It had a better effect. Magnitude was larger, basically, than the World Bank program. Now, this is not a sort of a substantive workshop of why this is happening and so on. We could spend some time talking about that. But essentially what we're seeing here is that this basically helps estimation, and we can sort of extract useful estimates that compare with the literature that has no image confounding in it. And in fact, we did replicate this. So it's a little bit hard for you to see, I realize, but what you're seeing here is basically different types of modeling approaches of how that F function, this image function, remember that F? How that is being represented, how it's representing, how it's distilling down information. And so we had a CNN approach, like classical CNN, a convolutional neural network, and we have an embedding model, meaning that we never really fitted a model, but we had another model that sort of extracted down some kind of a low-level representation of the image, and then we use that information instead. And we also had no images. And interestingly, we see that no images over almost all experiments are a little bit more positive, actually. So here you would be a little bit more confident in your effect. So usually, scientists are conservative in their estimate. Like the more conservative, the more we trust it, because like we usually are on the side of being wrong, right? So if you're a salesman, you want to be on the positive side. You want to sell stuff, right? You want to look how good it is, right? The scientists always like try to shoot down stuff because it might go wrong a million different ways. Joking aside, it's pretty like it's sort of saying, there's signals capturing the signal that the no image model has, but it's doing it a little bit more conservatively. So it means that there is some more information in the image space that is deconfounding the results a bit more. Why? Yeah. So that's the uncertainty estimates. Let's go back to the question of uncertainty quantification. So we're doing uncertainty quantification here, and so essentially there's just more uncertainty over that image. When you include images, it's more uncertain compared to the non-image model. I know that Connor, you ran a bunch of these particular analyses of the uncertainty quantification. This was just basically bootstrapping, right? We're not doing anything else in the uncertainty.
Correct. And the reason why some of the intervals look a bit wider is that those models use an approach involving randomized embeddings or randomized projections. So there's less optimization over the image representations. So there's an additional layer of variability since the model isn't being trained in quite the same way as with the CNN or a vision transformer approach. So I think that's what partially explains why some of the intervals are wider and some are narrower. It's the degree to which the image model uses randomized features versus learned features.
Thank you, Connor. Any other thoughts, reflections on this? Yeah, please.
But could you also, for each global trend, maybe pre-treatment covariate balance to see understanding the check, from like a traditional perspective, if socioeconomic development for really the thing between propensity scores that you calculate as
Yes, we did a bunch of sanity checks, like in terms of also the propensity distributions. We did basically as a checking the saliency map of these features of a low dimensional sort of representation of how much balance there is within the units. And they all, as far as I remember, more or less, I mean, Cindy did an amazing analysis in appendix that I can't recite at all. But I'm happy to, like, if you're interested in this particular study, it's not on archives. It's, again, World Development Review. As soon as the review is done, we'll put an archives version. So if you're interested, send me an email. I can send you that link as soon as it's up. But essentially, roughly, things look stable. Yeah. Okay. So this is an actual analysis, right? So, and then essentially, the game that we're playing is to think about, not only, basically there are two games that we play. One is to define how images enter the analysis, which took us a lot of effort in a way, right? To understand and to argue for and the value and so on. And then comes the other step, which is the modeling step. So that this F function is retaining information in a useful way. Now there's this trade-off. Usefulness is important, but as you'll see, there'll be computational bottlenecks. So it's really hard sometimes to run these models on your PC. But if you don't have a cluster, the question is like, how do I, still make something useful out of this, right? Within my computational limitations. I was debating with myself, like, how much emphasis should I put on computer vision? I mean, this is like a massive area of research. People spend lives and careers on this, and it's a fantastic area. It's very active research. Obviously, if you know what NVIDIA is doing, the stock has been going good for you guys. If you've been buying some NVIDIA stocks, I mean, it's basically largely based on what computer vision and deep learning in general is doing. But NVIDIA is investing a lot in computer vision of reconstruction of worlds. I mean, it started as a gaming company, right? The gaming was the focus. Gaming, not a gaming company, sorry. Building GPUs for gaming, that was the main thing. So they thought a lot about computer vision primarily. Now it became sort of used for general deep learning training, which was sort of a lucky shot for them. But however we think about computer vision, it's sort of ultimately think about this as sort of as a summary tool, right? As we would use summary statistics for a tabular data, we would use filters and other functions that transform our data in a way that is retaining information. So there's this whole sort of area of computer vision that comes from signal processing that is all about that signal to noise ratio analysis. And there are, a lot of really interesting recent work that we can point towards. But really what I want you to sort of take away from this is that, I mean, how many of you have worked with a convolutional neural network, just by a show of hands? Okay, so a lot of you. Okay, so you know a little bit what's going on here. It's basically a summary tool over the image space. But that's a different workshop altogether. But really, one of the use cases for causal images package is trying to simplify that process of selecting those functions F for you. So we have a I'll be showing you in a minute the tutorial of basically you use a transformer within a causal images, but also an embedding. But maybe this would be time, Connor, if you want to say something about the plan that we have for the functions that we're planning to include in the causal images and that are already included in this in the current setup of the package.
Sounds good. I could say a few words about it. So there are a number of tools out there for working with image data. There's PyTorch, there's TensorFlow, there are a lot of pre-trained models that you can download on Hugging Face and implement. I think those are great resources, and for some of our research, we've used those too. So, for other more custom modeling strategies, we found it useful to build our own package. So the package, it does implement a few functions that we found useful. So one of them is basically writing the image data to an efficient representation on the on your hard drive. So images, one of the bottlenecks when training models on images, or even just reading in images for some sort of descriptive analysis, is that loading into memory pipeline. So an image, it might be, a few megabytes, it might be a big image, might be a few gigabytes. Getting that from your solid state drive, which stores all your data, into your memory for processing, that process can be a bottleneck. So we were working with the training pipeline earlier, and 50% of the bottleneck in terms of the wall clock time was just reading the image into the computer to then be further processed. So this represents a big bottleneck. So one of the things that Causal Image does is it basically provides a series of utility functions for taking your image data and saving it in what's called a serialized format. So instead of your images being stored in random places on your computer, it stores them in one tight packed container, or one tightly packed depot for your computer to more efficiently read them into memory. So this drops down the bottleneck, at least in some of our pipelines, down from something like 50% to 1% of the clock time. So big picture, we have causal images to help with reading your data into an efficient format. We also have some functions that you can use to train custom models to analyze treatment effect heterogeneity, which isn't the focus of this talk, but which you can use when working with RCT data. If you want to figure out how different sorts of people in different sorts of places might respond differently to an experiment, to a treatment based on EO features, we can help with that. There's also a function for analyzing confounding dynamics within the same sort of framework that we're talking about now. Or if you just want to do a predictive run, we also have a pipeline for doing that too. And it exposes some of the high-level choices that might not otherwise be exposed. For example, in building these neural networks, there's a key part of that process, which basically controls how much weight you give to what's called the residual path versus the nonlinear path within these transformer backbones. So we expose a lot of these choices that might not otherwise be exposed for building more custom models. You might want to build your own custom model too, and feel free to fork the code or take what you find useful. But we do use a JAX backbone, which is pretty optimized not only for GPUs but also for CPUs as well. So on my computer, the GPU is faster, but only by about maybe 2x, because we're using efficient XLA compiled kernels for performing some of these matrix multiplications and at times convolutions. So that's a high level overview. So maybe I'll throw the ball back to you, Adel. Following up.
Thank you, Connor. Thank you, Connor. And then so essentially what we have here, it says Connor is saying, and I want to, by the way, before I continue, so we have, is the workshop 4:30 ending or is it 5? Yeah. As I think it said 3 hours, and then in that case we should be ending in about 15 minutes. Otherwise, it's 45. But it's on to 5. Okay. So good. And let's continue then. Connor, I think you are. If you can mute yourself, please. It's not you. It's someone in the background. I would love hearing your voice, obviously. So it's okay, cool. So let's. One thing that Connor will show you in a minute also is like basically the code set up for the causal images where you would sort of manipulate these different arguments. And after this slide, I'll be showing you some of the work, like how you would sort of set up some simulation systems to analyze the usefulness of images in your sort of fictitious system, such that you could sort of make better choices about the selection of computer vision models. Now, there's one thing with image data that is sort of particularly sensitive to variances of perturbation. Okay, so I'm going to say one thing here, and I'm going to do something else in the workshop. Basically, we're saying don't flatten your images, meaning that don't take these pixels that you have, 1024 times 1024 will give you about 100,000 plus variables, because there is perturbations such that these units, the meaning of the covariates, if you flatten some in left direction and some others in right direction, such that they would yield a wrong result. Okay, so essentially what you want is a better way of handling images. That's sort of the plea for computer vision. You want a way that is invariant to perturbations, right? That's the game that CNNs and transformers and other algorithms, deep learning, help you with. Now, let's do the following. I'm going to do a little bit of a tour in terms of a simulation setup here for you. But before we do that, I'm thinking we should maybe take 5 minutes break. You want to keep on going and maybe end a little earlier, or would you like to take a break? Take a break? Who would want to take a break? Okay, let's do 5-minute break, just stretcher, and then we can back. All right, so let's start again. So let's do the following. It'll be fun. So what I'll be doing here in this particular script, I'm going to create an image, and I'm going to create a handmade image, meaning that I'm deductively specifying rules that is going to draw a house for me. Okay, I'm going to show you houses. And why is that interesting? Well, what it's interesting is that I'm going to also generate these confounding units for me, and then I'm going to generate basically a causal system, right? A Y, a treatment, and a confounding. And that confounding, I'm going to use to construct the house. I'm going to draw the house, and I'm going to use that unobserved confounding. It's unobserved for my downstream model, but it's observed when I'm creating the image. Then I'm going to hide this confounding from the model downstream. And then we're going to ask ourselves, we're going to do some kind of transformations. I'm going to ask myself, how well will a downstream machine learning model detect the signal that is in this created image? Okay, that's the setup, right? And then we're going to compare different models, and then we're going to see, okay, so what did actually happen? Let's see what do we learn from this system. Okay, so I'm just gonna load in some base libraries, and all of the scripts I'm gonna make it available for you so you can play around with it at your free time. I'm gonna create an image that is 50 pixels wide, and its height is also 50. Okay, so basically 50 pixels and the height, and 50 in the base. And this is here defining a function such that I can display the image for you in ggplot. Okay. By the way, how many of you use R as the daily driver? Okay, yeah, so sort of 1/3 approximately. But ggplot is like the main visualization tool, I would say, in R. And here I'm going to generate the house function. So I want to just talk through some of the parameters in this function. So what you see here is that this function is going to take the U value. U stands for this confounding. And then it's going to affect, so each unit has its own U, obviously. It's going to affect the base brightness of the house. And I'm going to display it for you in a minute. Okay, so that's the way this confounding is going to enter the equation. Now, we don't need to go over all the details in this function, but essentially, it's a house drawing function. Okay, and you can create whatever image you want. So you can create a cat or a dog or so on. And there's a more advanced version of this data generating process where you can use a generator, basically generates an image from any of these expensive models if you wanted to create more realistic looking images. Here, I'm going to also do one thing, which is to define a blurring function. So I'm going to take this image that is non-blurry. It's going to be a house. And then I'm going to define a kernel such that basically a convolution that is going to blur the image, right? Because I want to do 3 experiments, one with the actual house, one with a blur, but it's a systematic blur. I'm going to apply a deterministic function. And then I'm going to do a noisy version. I'm going to take that blurry and I'm going to add Gaussian noise to the pixels. Those are the 3 setups. So the applying controlled blur is basically, yeah, it's controlled. And the kernel size, it's 17. So it's pretty large. Basically, it's a large kernel, and it's going to average over a lot of information in this image. Okay, so we did define that. Oops. Let's see there what happens. I'll press too many buttons simultaneously. I'm going to apply this. And this is the data generating process for the tabular data. I'm going to only create 200 units. This is just for the sake of it running a little faster here. And in the realistic setting, you'll have more. And the confounding that I'm going to generate is a binary variable. So it's a 0 and 1. Then this binary variable u enters my function in drawing the probability of the treatment. So this is sort of the true propensity, if you like, with some added little noise. So, and then the treatment is binary as well. So nothing mysterious here. Now we also see that the y, the outcome, is a function of the treatment with a 0.7 causal effect. This is the true effect of how y is generated. And then it's also a function of u being the treatment being 4 here. I'm going to, for the sake of making this a little bit realistic, add a tiny little bit of noise from a log normal density. There's nothing important for you to consider, but it's basically just making it adds a little bit of variation across units in this image space. Cool. Create the data, and now we're going to apply this house drawing function. So now I drew the functions in the background, and what I'm going to do in the next coming of rows is that I'm going to draw these things for you, so you're going to see them, and I want you to guess which of these images will yield the best effect. Okay, so clear image. We're going to add this systematic blur here, like this. And now the actual generation is happening. And then in this other part of the chunk, I'm going to filter out. I'm going to take out basically the image that has the worst effect and the highest effect, just to see the contrast for the visualization's sake. And then I'm going to plot this in ggplot. And so give it a minute. And then after that, we're going to do the modeling step. Basically, we're going to take this image, these images for each unit, and we're going to flatten them. But because there are no perturbations, it's going to be fine for the setup. But it's just a way of proving to use the classical approaches of these algorithms to see if we can retain that causal effect of 0.7. So let's do select the highest, the lowest. Basically, what we're doing here, it's easier if I show you. So what these chunks of code did for us was basically, I'm going to zoom this in if I can. Oops. There we go. All right, so what do we have here? So basically what I promised, we drew these images with that function that I defined for you. The high U, the confounder, controls the base brightness, right? So we basically, and then we selected just 2 units. And then we, based on that image, applied this blurring function, right? And then for each pixel, we added a bit of noise, a Gaussian noise. Now, I would like you to think about this. So you might say, clearly, we would be able to estimate the causal effect if we gave it the image here, flattened version, to these. We're going to give it to a lasso, to a random forest, and a perceptron model with a PCA applied on top of it. So who of you would say we would be able to estimate the causal effects of, using this image, that image, and that third blurry image? of 0.7.
So just wondering what kind of causal effect would you try to estimate here? I just come from more applied regression analysis.
Yeah.
When I'm looking, I mostly have an hypothesis.
Yes.
Have some idea about what kind of variable I want to test.
Yes.
In this case, I'm still a bit confused about how that.
Yeah. Got you. Yes. Yes. Fair question. Fair question. So let's do this. So let's go back to the data generating process. So essentially what I want to estimate is this 0.7 parameter. That's my parameter of interest. It's my tau that I've been calling tau. And it's the data generating process. We know what it is. But the true model has u in it. And so what I'm going to do is I'm going to hide this u, right? I'm not going to have it there for this model. I'm going to give it the image instead. And I'm going to give it I'm going to run 3 touch experiments where I give it the clear house, the systematic blur, and the noisy blur. And I'm going to ask myself, for which of these experiments will I be able to retain the 0.7 parameter? Is that clear?
The image as a way to control for confounding.
Exactly. Exactly. So would yours take a stab at this? Well, hopefully all of you to some extent. I just think out loud. That's fine. It is could be a hard one because we haven't done this. This might be the first time ever we doing this, right? So would we be able to get a reasonable estimate using the house image?
So you're trying to estimate a real house.
No, I'm yeah. So the parameter is still this 0.7. So I'm gonna try to retrieve it, but I'm gonna ask myself, can I replace this u that was now it's hidden, right, for the downstream model? It's only present in the data generating process in creating the house. But now I'm gonna get into the next step. I'm gonna hide this u, and I only have 3 adjustment sets to play with. And I'm gonna ask myself, how well can I retrieve 0.7? That's it. And so my question to you is that basically, how do you think this performance will go? Yes, please. Yeah, please. No. So it's basically it's a very important question because we essentially have a data generator. You remember the DAG I drew, and I just want to try to find. Let's just do this like this. Basically, what DAG do we have here? What DAG do we have here? What the DAG we have here is essentially we have u that went into generating x, right? And then both x and u went into generate y. Cool. Now, when we created the house, this image, only m entered the equation, right? Never did it touch x or y. So this is the data generating process. Now I hide u from u, so I'm gonna do this. Okay, and then I'm gonna ask myself, how well can I estimate this tau if u is hidden but only m is available? That's the game. That's clear? Okay, cool. Yeah. That's the game we're playing. So, and that's the confounding case, right? That's this confounding. I just told you, well, the past hour or so that the game we're playing is basically a game of confounding, of adjusting, and see how well we can retrieve the causal effect using M. And in this instance, we have no annotation. We're not giving any annotation at all, if this house being bright or not. There's no text. There's no other information except for the pixels. That's what enters the my downstream estimate. Okay. Great questions. It's a tricky one. I think what's like.
Well, I guess it's just a bit the clearer the better.
The clearer the better. Okay, that's it. We have a hypothesis. Great. So one is saying clearer the better. Anyone that wants to argue against that?
Both clear and the systematic blur, I would guess probably it's gonna be easy to retrieve that value. But
Okay.
the noise maybe not so much.
Okay, we have a new bid. Why would you argue, like maybe you want to give an argument?
Great. Systematic blur, the algorithm you're running will be able to kind of see the systematic nature of it.
Okay, we have a theory for the hypothesis, why that will be the case. We have a new bid here. So what we're doing in the downstream analysis, I should be clear on that, is that we're actually doing what I told you we shouldn't do, which I'm actually flattening the whole image. So I'm taking 50 by 50, so I have 2,500 covariates now. That's what I have. And I'll add a little bit of a cheat there. Reasons I'll explain later is that I'll filter out some non-variance containing covariates. But there's a particular reason why. Yes, but that's what's happening. I'm doing exactly what I'm saying I shouldn't be doing, but I'm doing it for the sake of ease and fastness. Okay, no more bids? You have a bid? Okay, let's look at this. So we have two bids. One is that, there's basically a scale, and then another bid is that, hey, basically clear and systematic, they should be very close to each other. Whereas the noisy would probably be a little bit outside of the scope. Okay, let's check. So now, because it's a similar data, we can actually check our intuition. And what I'm going to do is that, as I said, I'm filtering out some of these non-variance pixels. It's a little bit of a cheating, but I'll explain later. So this is just a function calculating how I calculate the average treatment effect. Essentially, that function, that mean difference that you saw in the China World Bank, this is exactly what this row 128 is doing. It's taking the weights that we estimate and then calculate those effects. Okay, and then I define a result list. I'm gonna run the base models. I'm gonna estimate the oracle, meaning that I'm actually giving it to you just as a benchmark to see what happens. Naive, I'm going to fit a model that doesn't see U at all. It's basically only regressing Y on X. So that should be biased, correct? And then I'm going to run a lasso model. Like, look at this. I'm reverting to classical machine learning. There's not much fancy going on except for the perceptron. And I'm going to run a random forest. And then we could have run a vision transformer, but it takes a little bit of time, and there are other reasons we don't want to include it for now. And I'm going to just do the visuals. Okay, let's look at this. I'm going to create it now. Great, so let's see. This looks, I don't think I have it here, the true one. That's the result. What do we have? What do we see? So these are all the models. We have the clear image is the filled circle. We have the systematic blur, which is the empty circle, the noisy blur, and then we have the colors of the different models. So oracle is a true effect. It's very close. It's only 200 units with some noise in it, but it's fine. It's there. The naive is off as expected. The lasso is spot on. It's doing pretty good, both in terms of, so it's slightly underestimating the effect with the clear image, and it's slightly overestimating with the systematic noise. Okay, and then we have the perceptron doing also pretty good, and both the clear and the systematic is spot on. The random forest is totally off, except for this one. But I would say that's by chance. I'm ruling it out, but what's going on? Let's just meditate over random forest for a while. What's going on here? So what's likely going on, and we have seen similar behaviors, is that when you give the random forest high dimensional data with many covariates and few rows, it has a really hard time figuring out these effects, because when it grows the tree one tree, it randomly picks two variables, right? And then it grows that branch and keeps on doing this, like 2 by 2, and it keeps on doing it. Never sees the whole data. It only sees the whole data when you average over the forest, but never in one particular tree. Whereas the lasso, it sees the whole covariate space when it fits the parameters, right? So the lasso sort of sees more, and it does this fitting quite efficiently. But why would you say it's here? Well, I would say it's basically, if you see the order of magnitude of how things are set up, there's basically a bias estimate with the systematic blur, and it's just following, everything is shifted downwards. So even the systematic blur is following with it. So that's pretty cool, right? It's with an image like this, handed in with this pipeline and this very simple setup, we're able to retrieve information that we wanted. Please. Yeah. Absolutely, yes. Exactly. Yeah, yeah. No, that's right. So in a way, perceptron had, and this was, me setting up the simulation, parts of the quirks when you start asking questions that obviously, yes, random forest would do much better if it had the PCA estimate. The perceptron model had it. The lasso didn't have it. So it's in a way a bit of cheating for the perceptron model. The thing is with the perceptron, and this is part of like setting things up, it was struggling with some of the pixels having zero noise. So in a way, it sort of faced a similar challenge as a random forest. So yes, absolutely. There's basically a lot you can do to pre-process the data such that you could, as you are sort of alluding to reduce down the space so that it becomes more efficient. Definitely, definitely. Yeah. Any other reflections on this? Marcus, please.
Yeah. All right. Could I ask you a question about
the
PCA features?
Yeah.
If you looked at them? Because it seemed to me that you could reduce all the signal into just the color of the facade, so basically to a single feature, right?
Yeah. So if you know where the causal effect is, where to look for it, you would obviously do that. But the thing is, in the summary step, because we're throwing away U, I mean, I know what U is. I'm basically playing God, right? But if you wouldn't know, like, where would you search? I think that's the key thing. And then the question is like, oh, I'll maybe just let my PCA reduce down the information in this lower dimensional space.
Yeah, I'm curious what they look like, because I feel like it should be, maybe you would actually like reduce it down to just a single meaningful PCA feature component, and then everything else would just be.
Might be, yeah. I mean, we can look at the PCA. One can look at the PCA basically variance and look at maybe it's actually just finding that one. Basically, you're saying it's finding that one vector that summarizes all this information.
Yeah. It's like given that everything else about the house is the same except for the facade. And I mean, you could summarize all the information if you just add up all the pixel values, right?
Yeah. Yeah. I mean, it's again, I agree with you. I mean, it's sort of a simple simulation, right? But the cool thing that we actually created an image, right? It looked like a house. It was an image, right? Then we can sort of manipulate the system. Now, in an advanced setting, we wouldn't know where to look for, right? We wouldn't know where to go. And also, there is a reason why, I mean, we're using these simple models to highlight that, traditional models can help you, but they helped us, like me guiding them, like I was basically supervising the feature engineering for them in a way, like basically throwing away those pixels, remember the code? That was basically feature engineering, because they were struggling. If I gave them a lot of information, the full 2,500 pixel space, you wouldn't get this nice result. So that's where deep learning is helping you. It's sort of feature engineering for you, so that you don't have to search for that space where information is yielding. Now, that's where causal images is coming in, and I want to hand it over to Connor here if you want to show how that plays out, maybe at sort of line by line, Connor, on the with the World Bank example stuff that you have there.
Sure, and I don't think we have a ton of time, so I'll just share this first. So planetary-causal-inference.org is where we'll post all the materials from what we've talked about today. So if you just go to the page and then click on tutorial here, that'll bring us to this page. And at the bottom, there'll be this resources area. That's where we'll post links to everything. We'll have the slides. We have some of the tutorials ready. Some of the data assets that you might be able to use in replication studies or in extending some of what we've been talking about also. So there is a tutorial in the package on the GitHub, causal images tutorials. And this is another simulation that uses the causal images logic. So maybe I could just stop sharing my screen and share my R session to walk you
maybe
through
Connor,
that.
I want to stop. Shall I stop my screen or you want to talk through my screen? What's the easiest?
I could pull up this. Do people see this? Do you, do you
No, let me just stop sharing. I think I need
Okay.
where is Zoom? Here we go. Sometimes Zoom just disappears. Oh, there we go. Thank you. There we go, Connor. Good to
Sounds
share.
good. Sounds good. So I'm not sure if you saw this before, but this is this is the site, and then right here there's a button tutorial. So if you just click that, you'll be brought to this page here where we have on the bottom a lot of the resources associated with today. So we have links to a Hugging Face, which is where we post really all of the data assets that we use in the research. So that could be data where we've linked RCT to EO representations. That could be data from some what Marcus has been up to with the poverty mapping. So we have the Hugging Face. We also have the GitHub here. So this GitHub is where we have the causal images code, where we have various tutorials for getting people started. If you do want to use this, we have been spending some time trying to get, a good pipeline going for us, and hopefully it's useful to other people as well. But there is this simulation in there where we just walk people through the various steps involved in getting this up and running on your machines. So there is the package lives on this GitHub. So if you install the package through GitHub, and then if you load it in, the next step will be building the backend. So this uses JAX as the backend. So downloading some various libraries that are required for that backend is all done automatically through this build backend call. If you are on custom hardware or if you are on a cluster, there may be some challenges there. Getting all the different GPU drivers up and running can sometimes be a challenge, but for most cases, it should be hopefully straightforward. Let me know if you do have issues. And then in this simulation, we do something similar to what Adel was talking about, where we have a ground truth, where we run an analysis with confounding with the images, and we see how well we can do recovering the ground truth from that. So just very briefly, I know we only have a few minutes, so one of the key things that we'll first do is write the TF record. The TF record is what's called a sequentialized data format, which is a very efficient way of writing on your disk the image corpus. This speeds up training a lot. If we didn't do this, what would take 5 minutes might otherwise take 15 minutes. So it reduces that pipeline, that bottleneck by a lot of reading in the images. So this is the first thing we'll do. We'll write the TF record. And then the second thing we'll do is we'll analyze the image confounding. So we'll basically add in the treatment vector, we'll add in the outcome, we'll add in covariates optionally, and then we'll add in a specification of where we can find that TF record. So one of the cool things here is we're doing multimodal ML here, since we have the images and we have the tabular data, and those are being applied. We're applying cross attention to those. So it's basically a fusion of the image with the tabular data, allowing the image representation to be different depending on the tabular variables as well. If we do give it X's, we don't have to do that, but it's just an option. So that's one of the things that this sort of approach can do that just the vanilla kind of vision transformer architectures on Hugging Face won't be able to do. We also expose various modeling parameters. There is some art to this. So if deep learning were easy, it would have been figured out in the 1960s, a few years after perceptrons were invented. But it's not necessarily always easy. So there is some experimentation involved and hyperparameter tuning involved, and things like the learning rate and things like the number of stochastic gradient descent iterations. So the package has some documentation for that. Let me know if you do have challenges there. And in this simulation, when we do run the full pipeline, we get these loss curves that look like this. When we're trying this, we get basically a reduction in the bias when we use the images, and so forth and so on. And we could experiment with how these different hyperparameter choices affect that overall result, among other things. So that's just a very brief tutorial for it. We just don't have time to go too much into the details, given how we're ending pretty soon. So maybe I'll just throw the ball back to Adel for wrapping up.
Thank you so much, Connor. I'm sure all of you in the audience have a lot of questions, but you know, this is really introducing and just getting to know the work. And then let's see. I think I'll just jump. Yeah, I think I'll just jump towards the end. I wanted to do some kind of a shout out for Marcus's presentation in 2 days. He's going to show you some of the basically the debiasing of these estimates. How do you think about that? And that's on Wednesday, right, Marcus? It's tomorrow. Let's see. Okay, so I don't want to miss that too. So, okay, so maybe I'll end at this little slide here if I can show it. Well, nonetheless, I think it's too many things. It's showing here? Okay. Yes. So I want to just briefly, thank you all for coming. And this is our, as Connor has shown, the various websites. This is my email. You have Connor's email. You have Marcus's email on Chalmers website. If you have any thoughts, ideas, feedback, would be delighted to hear back from you. The Substack is a way for us to communicate, but please send us thoughts and reflections also on how we can improve this workshop for future occurrence. And one little shout out is for the Journeys of Scholars. So I run the Journeys of Scholars podcast that has been a little bit dormant, but we have a bit of sort of really cool interviews with a variety of different sort of scholars across computer science, statistics, social science. The latest one that came up with was Michael Jordan, statistics at Berkeley. It was a really intriguing conversation there, and also Judea Pearl was on before that. So yeah, keep an eye on that, and thank you so much.